Zach, congrats on the first. Winner, winner, chicken dinner. Slim. Well, hello, Mr. Space Smiley Face. Thank you so much for the raid. Hope your stream was good. I was working on you a bit. Okay, let me take that away. So yeah, for anyone who's new here, I'm Dom. I do math help streams and video game streams, and on Saturdays that you're just seeing the beginning of now, we do some general relativity like reading group. I'm about to get into a Discord call with some friends, and we're gonna solve some problems together. Hey, Jasu. But yeah, so this is our first meeting on chapter 4. Principle of special relativity. So we're not into the actual general relativity yet. We won't be for a little bit. I guess maybe in chapter 6. But regardless, I guess let's go and hop in the Discord call. See, we got FizzBuzz waiting. Hello, hello. Fenbox is in here too. All you are on mute.
Hope it's going well.
Oh, hey. Yeah, it is. Hope you are too.
Hey guys.
For sure.
Hey,
Hey,
Fenbox.
Fenbox.
All right. Thank you all for being here. So, chapter 4.
Of course, thanks for having me.
Yeah. Oh, and for anyone who's watching, we have Hembox fan here who doesn't stream, but we also have FizzBuzz who does stream, so check him out.
I've got streaming envy.
I would love a Fembox stream.
Yeah, I'd tune in.
But until that happens. Okay, so I guess thoughts on chapter 4. This was our first meeting on it. I don't know that I have all that much to say about it. There's definitely a lot happening. I'm just scrolling through it. Oh, the thing with the rocket as like a demonstration of simultaneity being lost, depending on like with two people shooting a laser into the middle of a rocket, and in the frame of the rocket, it's simultaneous, but if you're observing the rocket, it's not. That was kind of neat.
That's confusing.
Yeah, especially because like light is a thing. It's supposed to be like invariant, if that's the right word across frames, but it kind of makes sense, or at least I was able to like figure out why that happens after thinking about it for long enough. What else do we have happening?
Oh, I loved that train schedule.
Oh, I didn't find that all that helpful.
Great.
I didn't know what was going on with that, to be honest.
Yeah, helpful, not so much, but it was a cool picture.
Yeah, I mean, I guess it's kind of neat that you could think about that as a space-time diagram, but yeah, I kind of didn't worry too much about it. It didn't make all that much sense to me exactly why that is. It is definitely it's weird to think about with space-time diagrams in general how you have that kind of constraint for the slope because you can't go faster than the speed of light. So it kind of like your space-time diagrams can't get too crazy. It feels like the tangents always have to have a slope of like less than 1 or exactly 1 if it's light. That feels like it's going to take some getting used to.
Yeah. The way that I think about it is in a space-time diagram, you can draw anything that you want, right? So you can draw, like if you're drawing a tachyon, right? that travels faster than light, then sure, that's over 45 degrees, and
Oh, yeah.
that's like a well-defined line that you can draw, but it's not matter, right? So any like position of a point particle over time has to stay less than 45 degrees.
Okay. And then just before this, I was trying to mess around with hyperbolic trig and like trying to get something with theta by actually getting the arc length of hyperbola and dividing it by the distance from the origin, but I got an elliptic integral and it wasn't pretty.
Oh man.
So maybe that's a lower, like I should find some type of resource that like talks about hyperbolic trig a bit more, like how to get all these like important numbers. So I think there's also a thing where like the angle theta is equal to like double the area underneath that line or something like that.
Yeah, I think that sounds right.
I was trying to get that too, but I got in a slightly less ugly integral, but still pretty ugly.
Huh.
But I'm sure there's a similar way using properties of hyperbola that I just don't know. Or I assume there is.
Yeah, pretty much all the like double angle formulas, half angle formulas, like everything. There's analogs of it with hyperbolic trig. It's kind of fun to work out, but it's not the most useful.
Okay.
I guess here it's very useful, but it's like not useful memorizing for tests and stuff.
Okay, fair enough. Yeah, I guess it seems like it only comes up in the derivation of stuff, and you don't have to use it all that much
Yeah.
to actually calculate. Okay.
It must be telling us something about the geometry involved in the Lorentz transformation, right? I think
Mhm.
once you understand that, maybe something clicks, but it hasn't clicked for me yet.
Hey, Cook.
Which part tells you something about the Lorentz transformation?
This hyperbolic angle, because I was reading about that a little bit this week, and I realized that I didn't know anything about it. I mean, when I learned hyperbolic functions, and I didn't learn much about them, but I just always learned them as being defined in terms of exponentials. And I never really thought of any way you could use them geometrically, right? Like trigonometric functions, I'm really happy to draw a circle and think about an angle sweeping out some triangle inside the unit circle. So when I got sines and cosines, I'm in business, but hyperbolic sines and cosines, I realized I don't know. Yeah, I don't know how to think about them geometrically, really. And it's got to be something in terms of that hyperbola, right? You're parametrizing the hyperbola,
Yeah,
and I
yeah,
should,
exactly.
yeah,
So
yeah.
it's right. So the line element on page equation 4.17, right? That's a sphere in 2 dimensions. It's a circle. So you get angles, you get trig functions, right? Cosine and sine. Um, you can memorize trig constants of like special values on the circle. You can do exactly the same stuff, but now you have a hyperbola, and
Hmm.
it's cosh and sinh. Um, I guess there are probably special points. I've never thought about them, right? It's not really something people care about, but you could imagine like an alternate universe where people, hyperbolic children sit down and memorize their table of hyperbola constants.
And they're weirded out by
Um,
the regular trig functions.
Yeah.
yeah, exactly. But then the one weird thing is if you drew a right triangle, right, with this is a very funky way to think about it, but you can do it. Okay, well, a light-like line that's 45 degrees has delta x squared plus, or excuse me, delta x squared minus delta t squared equals 0.
Mm-hmm. No,
So
like
you can draw that
separated.
as as like a right triangle with a hypotenuse 0. One side length delta x, one side length delta t. But you have to interpret that in this weird hyperbolic geometry.
Yeah, and we did that. That was one of the examples in the chapter.
Oh, which
Example
page?
example 4.1 on page 57.
Oh yeah.
And they had the two triangles. In the second triangle, two of the sides were at 45 degree, or along those
Oh yeah.
45-degree lines. And when I worked out that what is it, the line element, when I got a line element of 0, I was like, I got to be doing something wrong here.
See? That's just the
That
way it
didn't make
works.
sense to me because if you're thinking of a line element, right? What are the units of a line element? Is it meters? Is that how I think of it? Like ds, it's measuring it's measuring a distance, right?
Yeah. And what the weird factor of c coming up everywhere is just saying that either time should be really measured in meters or vice versa. We could choose to measure meters in seconds.
Yeah, they talked about that at the end of the chapter.
It's super weird.
It is weird. What's weird is thinking of these 2 points on the space-time diagram that are clearly distinct, right? I mean, they're separated by a significant amount in the x direction and in the ct direction, but the ds comes out to be 0. I want to say if the ds is 0, they have to be the same point in some sense, but that's not right, is it?
Yeah, you're onto something really important, and this trips a lot of people up. I see Dr. Cook in here. I bet he he had stuff to say. He probably can't help himself.
Yeah, I'm in
but
Starbucks. So are you getting the background sounds? I don't want to just.
No, I can hear it.
No, I don't.
oh
I
yeah,
don't hear
I
anything.
can't hear anything.
Okay, but do you want to spill the beans then, Isbos, or should I?
Yeah, well, so yeah, the thing I can't stop myself from saying is this. So this delta s squared versus whether 2 points are the same or not. This is something that tripped me up for a long time, and physics books don't really tend to go into detail about it. It's the difference between the topology, like point set topology, and the geometry. So the point set topology gives you stuff like limits, and it gives you stuff like 2 points being distinct. So this delta s does not give you the topology. So it's not a metric like you would get in a analysis book.
Well,
Wait a second. So I was reading about the Lorentz boost also being called a squeeze mapping. And they said what you do is you compress it along one of the 45-degree lines and you stretch it by the same factor along the other 45-degree line. So I can kind of see that now.
And in physical terms, that's called the Doppler shift. So when you boost, if you move to this light cone coordinates, which instead of doing t vertical and x horizontal, you do 45 to the left and 45 to the right. That's like light going left and light going right. Then the Lorentz transformation is a lot simpler, and it just Doppler shifts light in opposite ways, just like you said, squeezing the light in one direction in terms of frequency and expanding in the other. And so that's actually one way, really nice way to think about the Lorentz transformation, is it keeps the area, the Euclidean area of diamonds constant.
Yeah.
Interesting.
Space-time volume, they talked about. This other book I'm reading, they call that space-time volume. They said that's invariant under the transformation.
And then another thing I wanted to add to what Fizbo said, so this is not like a metric that's usually meant in terms of metric spaces, because when people say metric, they typically mean Riemannian metrics, which are strictly positive or 0 if it's the same point. But this is a more general metric, or Lorentzian metric. So sometimes you'll see pure math books call this like Lorentzian metric spaces, where the metric can go negative, the distance between 2 points. And so here in space-time, if the space-time metric distance between 2 points is 0, that means they're connected by a light ray.
Yeah, exactly. But it
or at least infinitesimally.
they're not the same point. but that's allowed because you kind of distinguish between these two things, which is weird. It's not really how mathematicians teach it, or excuse me, treat it.
Yeah, there's just one good book by math. I think his name's Barnett O'Neill or O'Neill Barnett, something like that. It's well, sometimes instead of Lorentzian geometry, they'll also call it semi-Riemannian geometry. It's a synonym where you let the metric go negative. So if you search it that way, sometimes you'll find some pure math references.
To be honest, I got a little lost like partway through that. So like, but with like this measures the distance, but you can't construct a shape out of it, is what we were saying before. This is not enough information, like the.
So one way you can look at it is that there are like two distance functions, and this is maybe not standard, right? But one would be like the regular Euclidean thing, right? And so when you're doing limits, right, when you're making like an epsilon ball around something to do calculus, right? That distance is going to be calculated using like the regular delta x squared plus delta t squared less than epsilon or something. So if you were doing limits where you need to like make sure one point approaches another point, you would use the regular distance function. But the really interesting concept is that that's kind of distinct from geometry. So you can define other geometries, you can define other curvatures.
Okay, I get.
And one of them is.
It's a weird thing, I guess.
Do you mind if I go back and answer something, address something Fenbox brought up?
Sure.
Oh yeah, for sure. I think I'm
okay.
Distracting from your point, maybe.
He was asking about the interpretation of the space-time metric. That's a really good question. So, and whether it has units of meters or time. In relativity, you can just multiply and divide by c freely. So you can think of it either or. If you set c equal to 1, time and distance have the same units, in fact. But so we're looking at equation 4.9, right?
Oh, I brought this up because it was. I guess I think we're talking about like the general like line element, including delta y and delta z, but
yeah. So with
also
this
that.
sign convention, so the interpretation of the space-time metric depends on the sign of it. So if you have two space-time points called events, and if the space-time metric between them is positive in this convention, that means that's the spatial distance between those two events in the frame in which they occur at the same time. So for two events that have a positive space-time interval as defined here, there exists a frame where they occur at the same time, and that space-time interval you calculate is the distance between those two events spatially in that frame.
Oh, okay.
And I think so. That's one interpretation when it's positive here. But I think the more important one is the following: when it's negative in this sign convention, then it's the proper time elapsed for an observer who goes between those two events, and that's very important to know. So one way to really summarize in my mind the space-time interval for those events, those are called time-like separated, is the twin paradox. So when I learned special relativity in undergrad, I remember I always forget which twin was younger when they came back, this traveling twin or the one that stayed at home. And I always had to rederive it for myself. But if you understand the geometry of Minkowski spacetime, then it's really obvious because, well, actually, let's do a recap. Do you remember which twin is younger when they come back together? The one who went off, accelerated, turned around, or the one who stayed at home?
The one who traveled.
Yeah.
Yeah. Okay. Good. So you can think of that as just you can rederive that and using all the time dilation equations, but the better way to think about it is it's just a Pythagorean theorem in Minkowski spacetime. So imagine like a straight line versus you walk out a triangle and walk back on Euclidean plane. clearly the triangle path is longer, right? Because you deviated from a straight line. You agree with that?
Hmm.
Yeah.
Like a right triangle in Euclidean space, the hypotenuse is longer than both the legs because
Yeah.
But in Minkowski spacetime, you have this minus sign in equation 4.9. And what that means is when you deviate from a straight line trajectory, this will become a geodesic in a curved spacetime. But in simple flat Minkowski spacetime, if you deviate from a straight line, you actually get a shorter spacetime distance. And again, for time-like events, that represents the time expired on your personal wristwatch. So yeah, so it's called proper time, but I think a less formal, more intuitive name is wristwatch time. So the traveling twin is clearly younger because they took this deviation from a straight line. So in Minkowski spacetime, the straight line between two events is the longest possible spacetime interval, not the shortest like Euclidean space. So the twin who stays at home goes a straight line, therefore they get the longest amount of spacetime distance between the two events. And the traveling twin who has to curve around by taking a not straight path, Euclidean space, that would be a longer path. In Minkowski space-time, that's a shorter path because of the minus signs. And so one way to think about geodesics in space-time is, I've heard it called sometimes the principle of maximal aging. Another way to think about it is the lazy clock hypothesis, is another name I've heard. An unaccelerated observer in space-time will take the trajectory in space-time between two events that maximizes its own age. So the traveling twin is younger because they had to accelerate to turn around because therefore they're not taking a straight line path. But that's just another way to get some intuition about this minus sign and the twin paradox. You should really just think of that. That's really just the Pythagorean theorem in space-time.
Yeah, it's weird because you have a dimension you can travel in that reduces your distance, and that it's
Right.
weird. So it looks longer on a regular two-dimensional Euclidean space, but because there's the minus sign in front, you actually want to travel in that direction if you want to get the minimum distance, I guess.
Or just grab your Minkowski piece of paper and draw it. It'll be clear. But yeah, and in fact, distance is almost misleading because it is distance if you just think of this abstractly as a metric. But the physical interpretation of that distance in space-time is the time elapsed on the watch of a person who took that path. So if you draw paths in space-time, trajectories that people are traveling, the length of that path, as measured with this Minkowski metric, is how much time would elapse on their watch if they took those paths. And so even if they start in the same point, that doesn't have to be the same. Just like in Euclidean space, if I draw a straight line versus a curved line between 2 points, the distance could be different. The space-time interval, it's the proper time elapsed on the wristwatch.
And so that's figure 4.12, right? I mean, we're looking on, Don's got it on screen right now, figure 4.12, and that's the person who went straight. Yeah, okay.
So Alice's trajectory there with the Euclidean metric would be longer, right? Because every time you deviate from dy squared, you pick up a dy squared plus dx squared. So you're increasing by curving away from the straight coordinate line. You get a longer Euclidean distance because it's the square root of dx squared plus dy squared. So if you curve, you add an extra dx squared. But in space-time, you add a minus dx squared, or I guess with this sign convention, it's, yeah, anyway.
They kind of flip-flopped
Alice,
as it suited them, to be honest. Between which signs they use, but yeah, that's one they use more with minus CT.
Yeah, I like the other one. I like the time coordinate to be positive. Because if you're thinking about time-like observers more, then that's the better one, I think.
Yeah, I'm with Dr. Cook. Also, it's fun to argue about this stuff. A lot of people very passionately.
Well, okay, before I knew any relativity, I would tell people I prefer the mostly positive sign convention because if you look at constant time slices, you get just a Euclidean metric. But that's before I knew any relativity, and I really internalize what it meant. And now I prefer the mostly negative for the times as positives.
Interesting.
Yeah.
But so you're a mostly minus guy too?
Yeah. Yeah. And I don't.
Okay.
On the horrible bird site, there's a lot of physicists who prefer the mostly positive thing, and so I'm always the dissenting person, because it's fun when they have a comment thread going like, oh geez, it would be horrible to secretly be friends with someone who chooses the wrong metric signature. And I
Wait,
always jump in like, yeah.
where do you see
on Twitter.
Mm, mm.
Horrible bird site, yeah. There's some good cosmologists and physicists on there.
Since we are just talking about the twin paradox, example 4.3 has a really weird, like they give a simplified version that's easier to calculate where just one twin travels in a straight line, turns around, travels back in another straight line, so you don't have to deal with any curves. But they made this weird point about like understanding the instantaneous acceleration. I couldn't really understand the math that they were doing there, or like I feel like that no physics book I've ever read has ever really cared about this instantaneous acceleration. You just kind of neglect it. They're doing some weird like epsilon limiting argument that I just it felt unnecessary to me, at least. Maybe there's a point behind it. So at least I feel like the original like paradox is pretty understandable if you just don't care about the acceleration at all. Just kind of like let it be weird.
One of the other books I read explained that the reason it wasn't a paradox is because the person who flew off in the rocket ship had to be accelerated. I didn't really understand why that resolved it. Like why couldn't I be the person staying at home, and why couldn't I be the person on the rocket ship flying out to Saturn or whatever, and I see the Earth accelerating away from me, and I could say, well, I'm at rest and they're accelerating.
But no, actually, you can't. Acceleration is absolute. So the way you could know is just hang a pendulum in your hands.
Oh, okay.
The people on the Earth,
Okay.
it wouldn't deflect. On the spaceship, it would deflect. You would feel it. In fact, how would you feel it? It would feel like a gravitational field. And
All right,
that's
okay.
where that's like the genesis of general relativity. If you're accelerating reference to with regards to inertial reference frame, you perceive a gravitational field. So the twin that turns around, that moment during the deceleration, acceleration, they experience a gravitational field. In fact, that's another way they would interpret the age difference, because they would say they're deeper in a gravitational field than the twin at home, and therefore they'd say the twin ages faster in their perspective by gravitational time dilation. They're higher in a gravitational field, and you'll see later clocks run faster higher in a gravitational field. So that's the way physically the traveling twin would explain the home twins' greater age. They aged faster because they were higher in this gravitational field that the accelerating twin briefly experienced. Yeah, so I think what he's trying to say here in reference to Jed's comment is that if you take the limit that acceleration is infinitely large over infinitesimal small amount of time, you still get the same aging. And I'm just giving another way to see the same thing. I prefer the strictly geometric viewpoint. The length of these lines is different by the metric.
Yeah, I just kind of like thinking about the triangle and not digging too much into the physics or like into the acceleration piece, but that's also feel like a weird part for me. Okay, a weird thing I can't wrap my head around is if you have two space-like separated points, do you need to travel faster than the speed of light to bring them, like, to make their light cones overlap? Or, like, I have a hard time wrapping my head around, like, space-like separation.
Well, the light cones will eventually overlap, but the statement I think
Oh,
you're
yeah.
looking for is if you have two events that are space-like separated, for an observer to travel between one event to the other, they would have to travel faster than the speed of light.
Okay. So my phrasing was wrong, but the basic idea was there. Okay.
Yeah, I think that's what you meant. And you can just see that, like, if you plug 4.9 into the condition of 4.11a, you'll see delta x over delta t must be greater than c.
Okay. Fair enough. What else was there in chapter 4? Oh, I was very weirded out, like in figure 4.13 on page 67, like these different, they have an x in CT axis that are perpendicular, but then they have an x prime and CT prime axes that are kind of not. They're rotated and they're not orthogonal. But, and so that made me think of, start thinking like linear algebra, like linear transformations, but I think this is something completely different.
This is again a feature. The piece of paper you're looking at is Euclidean. They're still Minkowski orthogonal. So you compute inner products not with the Minkowski metric, but with, or sorry, not with the Euclidean metric, but the Minkowski metric. So I mean that's probably pretty mysterious right now, but they look orthogonal because the piece of paper. So they look not orthogonal because the piece of paper is Euclidean and failing to capture the proper Minkowski geometry.
Okay, and I saw later on this is like a kind of helpful visualization to show like how in one frame things can be simultaneous, but then in the other one you can find a distance between those two events. Or it's a delta t.
Yeah, so if you think of back to our earlier conversation about boosts, how Lorentz transformation encode the coordinates, how the coordinates transform when you do a boost. So when I say boost, that makes sense. Like you move from one inertial frame to another that's moving at constant speed, with reference to the first. Yeah, so the nice way to think about boosts, like if you're in Euclidean space, a rotation rotates everything along a circle in the plane XY plane. In Minkowski space-time, a boost rotates everything along these hyperbolae. And so in fact, that's why these coordinates x and t go to x prime and t prime. They're rotating hyperbolically on this Minkowski hyperbola of constant distance, like space-time distance. So what was I getting at? Right. So if you have 2 points that are simultaneous, that means they lie on a horizontal line in a Minkowski space-time diagram. And then you do a boost so they each rotate on their own different hyperbole. You'll see they'll no longer be on the same horizontal line. That's the geometric interpret. Yeah.
Figure 4.14 has an example of that. It's a little bit hard to see from their figure, I guess, but they're supposed to be on the same t prime line, but I guess the Euclidean page makes it a little harder to see.
You know what we need for this? We need some nice 3 blue, 1 brown type animation for this transformation. There's probably somebody who's put one together.
Yeah, you can find some online. Yeah, I'm away from my computer, but I can try. Yeah, actually, there's another
from me.
Oh, nice, man. Yeah, I'm sure you have some.
Oh, I think I remember you looked one before, Fizzbuzz, like a while ago.
There was a formula you had up where there's in the book. Can you scroll up? There's a formula where it was like the integration over the gamma factor. It was like right after the twin paradox discussion. I wanted to make an analogy with that too.
Page 62, maybe?
Oh, it's a tau AB equals
time dilation?
Yeah, 414. So that's just that's completely analogous to the standard Calc 2 formula, where you to find the length of a curve, you do the integral of square root 1 plus f prime squared. You remember that formula from Calc 2 to find the length of a curve?
Yeah.
This is the exact same formula. The only differences are we have a minus sign now because it's Minkowski space time, and it has a physical interpretation of the length along the amount of time that would elapse on a person's clock who's following that space-time curve.
Right.
But I don't know, making an analogy between this and the Calc 2 formula for Euclidean space was helpful for me. Because again, that's the revolutionary thing I think about VR. It's all geometry. Like the causality of space and time is like a matter of drawing lines on the paper.
Hey, Eldridge. Hope you get it back. I guess what is it the arc length of? I noticed that it looked like the arc length formula. I don't think I thought about it too hard. I guess it's the arc length of position with respect to time, or am I thinking about it too hard?
It's a curve in this t versus x diagram, this Minkowski diagram. Physically, that curve represents the trajectory of somebody in space-time. So you sitting in your chair right now, in your own Minkowski diagram, you're just moving up vertically along the t-axis. And you can compute the length of that curve that you're tracing out. And that length via 414 would correspond to how much time elapsed on your wristwatch as you went between those two events. But in your reference frame, you could see somebody accelerating, do some crazy curved path in your t and x coordinates. And you can compute the length of that curve in Minkowski space now with this formula. And you get some number. And you can convert a number of seconds, let's say. And that number of seconds would correspond to how much they aged personally going between those two events in the particular way they did.
Okay. I'm just scrolling through chapter 4 to see what else was weird. I think the end of chapter 4 is more stuff that I've seen before, so I don't think I had too much about. It was more like the earliest stuff that we've already talked about, I think, that was weird to me.
Yeah, I think he's here. My sense is that he's trying to show you familiar things with maybe a more geometrical viewpoint.
Yeah, definitely. Like I've seen the final results of like the Lorentz transformations, but I definitely have never seen that like the line segment stuff and like where it all comes from.
I'd never seen them written in terms of the hyperbolic angles. So that was the stuff that really confused me, but I think it'll make more sense if I think about it a little more.
When we get to the whiteboard, I can show you something which I think may help a lot, actually. An even nicer way to think about Lorentz transformations.
Yeah, like they just kind of like randomly did that, knowing that there would be some nice like symmetries. There wasn't a particular reason to bring them in other than the identities happen to work well with the minus sign. That's how I interpreted like where that stuff came from. But we do have a whiteboard up if we want to.
Yeah, I agree, but I would say that's fundamentally why cosine and sine show up as well.
Okay. Yeah, fair.
So like pretty much any statement that you make about hyperbolic cosine and sine, there's an analogous statement. So like, yeah, maybe it is something like trivial about the making the signs work out.
Yeah,
Yeah,
cosine
that
squared
same old
plus sine
trick.
squared is 1. And then cosh squared minus sine squared is 1, right? So I was trying to
Yeah.
draw some triangles. Yeah, when I'm doing trigonometry, I'm always drawing triangles and I'm very comfortable. But when I started trying to draw what I was thinking of as like a hyperbolic triangle, I'm like, I don't know how this works, and I don't know if anything I'm doing is actually legit.
Well, it's like what Fizbuzz was saying. When you're on the 45-degree line, the length of that hypotenuse is 0 because it's a
Yeah.
light-like ray. Yeah.
I think at some point the book kind of like
Well,
showed why sine and cosine like show up or like they can give symmetries in the regular like flat space time, just using the same like type of identities. But if we do want to go over to the Excalibur, I've got it open. The link is in the voice chat.
Yeah. Okay. I'll move there. I won't be able to see your Twitch stream though after I do that. Because I only have my phone and my iPad.
Biz Buzzington. Do you want to bring in any of the equations that we've been looking at, Cook?
No, actually, I think I can do this.
Okay.
I have a really nice way to explain why these hyperbolic functions are showing up. I'm just trying to get familiar with this.
No
I
worries.
liked what you said a
Okay.
minute ago, where if we were looking at two things and they're moving, or two points that had light cones coming out, and if they moved, they would both be moving along their own hyperbolas. That was interesting. I hadn't thought of it that way.
Well, okay, so let's talk about just Euclidean space for a moment. So, and if you're talking about like symmetries of Euclidean space, a really nice way to do that is with complex numbers. So let's say we have a complex plane z plus I, x plus iy, okay? And then of course we can define the conjugate. And this is really nice because then z star is x squared plus y squared, which is the distance. Okay.
The distance, right?
I just square the distance curve. Okay. And so we can actually rotate. We can do rotations in this plane very easily with complex numbers by virtue of this fact, because if we go z goes to e to the I theta z, then the length of that arrow is preserved.
Yeah. Because e to the I theta has magnitude 1.
Right. Or you can just think of e to the 0 after the exponents cancel.
Yeah.
Yeah. So that means I'm preserving the length of the arrow, and this is a continuous symmetry because I can vary theta continuously. So if you just think about enough, this must be a rotation in the 2D plane. And then you can prove the following just from Taylor expansion. Right, you've seen this. This is Demoivre's theorem, essentially.
Yeah.
Yeah. And so if you multiply, oh, why did that happen? If you then you can get the formula for rotation really easily just from complex multiplication. Scalidor really does not like my pen. Okay, and then you can interpret this as the new z prime. So this is x prime plus I y prime. So you instantly get like the rotated coordinates. X prime is x cosine theta. So this is a really easy way to do rotation without messing around with 2x2 matrices. If that makes sense.
Yeah, I got you so far.
Okay, now let's go to space-time. So let's now say I have, give me a moment. I want to get I want to match his convention. We had, yeah, I think you want to do this. So instead of doing I, the complex unit that squares to -1, we want to introduce this J, which squares to +1. And this is a different algebra of numbers called split complex numbers. But I still define the conjugate by negating the new unit, I suppose. But now watch what happens here. If I multiply these together, I get x squared. But now because J squares to 1 and not -1, this is minus t squared. And what does that look like?
Hyperbola? It's
Yeah.
equal to a
well,
constant,
that-
I guess.
Yes, yeah. But this distance more generally, this is the Minkowski spacetime
Oh,
metric.
okay.
Yeah, this is the distance between how you measure distances with Minkowski ruler. Okay. So how can I what continuous transformations of the Minkowski plane can I do to preserve this? Well, I can go z goes to e to the j theta instead of I theta. Because you see, then this will be preserved, the Minkowski spacetime distance, by the same math. Okay. But now,
Okay.
oh, what
No,
happened?
yeah.
Okay. But
I
now
haven't
if I expand this out using Taylor expansion, j squared is +1 now. Oh, that's not what I wanted. 4 factorial and so on. So you can group. And now, unlike the e to the I theta expansion, there's no negative terms here because j always squares the +1s. And do you know what these Taylor expansions are?
They got to be the hyperbolic trig functions, I guess.
Yeah, exactly. Okay. That is buzzing to And now we can see what this does for the coordinates. If we hyperbolically rotate with e to the j theta instead of just normal rotation with e to I theta, what do we got? Okay. And so this is x prime. This is t prime. And in fact, this is nothing other than the Lorentz transformation. If you choose cos theta equals gamma, which is 1/1 minus v squared. I'm saying c to 1. That means sinh theta must be, I think it's gamma v. If I remember my hyperbolic geometry.
I got
And that
gamma
means
v over c the other day.
I'm saying c equal to 1 here.
Gotcha. Oh yeah, I see.
This is equals v, or v over c. So I can solve for theta. That's arc tangent of V, and this is called the rapidity.
What's it called? Rapidity.
Oh.
So
Okay.
that's another name for hyperbolic angle in the context of relativity, and it's the arctangent of the speed. So when you hyperbolically rotate by a hyperbolic angle theta, that corresponds to a Lorentzian boost of speed v, where the hyperbolic angle theta and the Lorentzian boost speed v are related by this relation.
Hmm.
But yeah, if you just learn Lorentz transformations like in an introductory physics class, it's like this mess of symbols and it has no interpretation. But really, it's a hyperbolic rotation in space-time.
Yeah.
And I think this algebra of split complex numbers is showing why you get extension cosh. It's really because if you go back to the Minkowski metric, here, I'll write it again. The transformations between x and t that preserve this distance are hyperbolic rotations, just like the transformations that preserve this, what you might call a bilinear form if you want to be mathematical, are just the 2D rotations. So it all really goes back to this form of the metric. Okay, that was my rant. Thanks for coming to my TED Talk.
That was good. That was good.
That's really cool. You can like just do it with this J, kind of like alternate complex number, and it gives you all that.
Right.
What is J here? So yeah, I kind of lost where the J came in.
It's just like I, but it squares the positive ones, so I'm squaring the minus one.
Hmm.
So you can read more
if I
about.
were to add to this, I would say you already know how to work with J. Okay, so if J, I guess I'll add at the bottom here. J, whenever I think of this stuff, I have to translate it to this matrix.
Yeah, this is a representation
0.
of the algebra.
Oh my God, is this one of these Pauli things?
It's very close, right? It's like just like I can be written as this. Right. Then I squared is the negative identity matrix.
Yeah.
And if you J squared is a positive 1. So you're not using the fact that this is a 2x2 matrix. You're just using the fact that it has the algebra you want. Because it has the relation J squared is to +1. So you can think about purely abstract with just J, how I presented it. But if you want a concrete matrix, one virtue of just going straight to abstract algebra is I think it's you don't have to write 2x2 matrices. I hate writing 2x2 matrices. Like if I had to do a rotation, actually, no, this is a good point. Actually, if I want to build a Finbox FizzBuzz just for, if I write EVI theta, cosine theta plus I sine theta, so then I use his 2x2 matrix representation. Uh, 0, 1, -1, yeah. Then you just get the standard 2x2 rotation matrix.
Okay. Yeah, I love it. I love it.
Oh, and actually, yeah, so this is really nice. So if you go back and use his J, you'll get the 2x2 Lorentz matrices if you do my formula. Let's do this together. Oh,
And just a quick comment on the Pauli matrices. So yeah, J is not quite a Pauli matrix.
Okay.
I would say I is, right? But the Pauli matrices are a bit different.
so the Pauli matrices is this representation imposed on the quaternions. And you can think of I as a quaternion, one element of the quaternions. So the Pauli matrices are really just the quaternions in disguise.
Hmm.
That's the Lorentz transformation. Actually, well, yeah. I like boost better than transformation. It's more physical.
Mm.
He had a footnote in the text. He said boosts are a special case of transformations.
Yeah, because Minkowski spacetime still has rotational symmetry too. You can no direction is preferred. So you can do like a standard rotation between X and Y, or you can do a Minkowski, or you can do a hyperbolic rotation between X and T, and that has the physical interpretation of moving from one reference frame to another. That's initial reference frame that's moving at constant velocity.
Now, why are we allowed to let C equal 1? At
Just
the end of the
measured.
chapter, they said, let's let C equal 1.
Well, C is 1. What do you mean?
I don't know. I always thought C was like 300,000 million or whatever.
But in what units, right?
And what
Meters
units?
per
Yeah,
second.
yeah.
So if
Yeah.
I measure a distance in light seconds, then it's
Yeah.
one light. It's 1 second per second.
So you're saying instead of thinking of C going to 1, or maybe another way I could think of it is I'm taking all my my space dimensions and scaling them out by a factor of C, sort of thing. Like where I had 1 meter, I now have 3
Even more
times 10 to
simply,
the
I would
8
just say,
meters.
like, the universe is cold and indifferent to our choice of unit. So
Yeah,
the
yeah.
universe cares nothing about metric. Oh, sorry, meter. That's what I meant to say. So I'd say it's actually maybe to endorse FizzBuzz's comment a bit. To me, it's an indication that we as humans, we chose the wrong unit of distance when we chose meter. I mean, meter's a lot more convenient for us, but
Yeah.
it's not respecting this fundamental speed in some sense.
Okay.
So there's one book that had a really great analogy on imagine that we lived on some world with really high gravity, right? So like surface of a neutron star or something. And people who live on that world, they would want to measure vertical distance with totally different units, right? Because moving up vertically would be some absurd heroic feat, right? And they would consider the vertical axis fundamentally different from the other two horizontal
Oh, so you say they would
planes.
use one unit of distance for horizontal length and another for vertical lengths?
Exactly, yeah.
Yeah, okay.
And so then they would have some like miraculous conversion factor until eventually their physics was advanced enough they could look away from their planet and see, oh, in fact, there's a symmetry between the different dimensions. They couldn't see it from their like limited perspective.
Yeah.
But that their conversion factor between vertical units and horizontal units is imagined, and same with C.
It kind of reminds me of like measuring depths in the ocean. You can use feet and meters, but sometimes you use like what's that called? Leagues. Use leagues and
Leagues.
they're a different unit. Like you'd never talk about 10 leagues west, but you might talk about 10 leagues under the sea. I don't know. It's,
Okay, so, and then they had an appendix where they were talking. Don, did you read Appendix A at all? I just read some
Oh,
of it today.
I didn't realize that'd be relevant. No.
I guess it might be. We might have to look at it later, but they were talking about how to convert from the MLT system to the ML system. And then they said later we're going to go to just an L system where we let capital G equal 1. The gravitational constant is also 1. and everything's measured in length. Get this. We don't have any mass anymore. But I guess we'll worry about that later.
Yeah, I'm
You know,
already
and
weirded out
that's
by.
great.
Go on.
Sorry, go ahead.
Oh, I'm already weirded out by just missing the T in MLT. Going down to just L is gonna feel even weirder.
I always wonder, like, after studying this, why don't cranks, physics cranks always say like, oh, everything is vibrations, and they really focus on that. Why don't they say everything is meters? Like, I want to have a crank say like, no, I figured it out. Everything is distances. But I think vibrations are more fun. They focus on that instead. Just me? Okay, well. So I have to go. If I could offer one last comment, it would be that I really, really recommend Einstein's 1905 paper. Like,
Oh,
it's
Okay.
actually it's really good. In my opinion, it like instills the virtues of a physicist in a way that a lot of modern physicists have missed out on. So if you read this, you will be better than some modern physicists who you might read about in Nature and this and that. But it's a really good paper. Yeah.
Okay, that'd be cool to read just for, like the historical like purposes, but that's cool that it's still like relevant in that way.
Yeah,
Have you
I'll
read
make sure to post it in the Discord.
Yeah, please do.
he wrote? Have you read his popular summary of relativity?
No,
Relativity
I
to
haven't.
special and general theory.
I haven't.
That,
That's
that's what got me. That's what got me into all this stuff because I was like in the penultimate year of the condensed matter theory PhD, and I just picked that up, and it got me obsessed with this stuff. And he wrote for a general audience. I think I want to say 1921 or maybe earlier. But it's really really good. I don't. Yeah. But I think the general advice: read Einstein is never wrong.
Okay.
I'll have to make a note of that. Okay, I'm off. Thank
See
you
you,
for
Face
organizing
Buzz.
this.
Thanks for being
See
here.
ya.
See you later. Do you want to do some problems?
Yeah, sure.
sure.
Unless you have anything else. Okay. Prime asking, do we study Maxwell's equations and tensors? Maxwell's equations we kind of did separately last year, and tensors, I assume we're going to be introduced to some basic ones through this book, or the basics of tensors. Okay, so I for the problems for this chapter, I mostly just kind of did the ones without any of the special letters with them. I did some, but I mostly stayed away. So the first one I chose was number 2. All I just did seem on the shorter end. Let me bring it in. Hey, Sakno.
So you've already done these problems, or you just picked them?
No, I have not done these. So if you have one you like to suggest, Cook, if you have the book available, like please do. But I just kind of chose ones that seemed reasonable enough for us to do. So at the bottom here, I brought in number 2. Hey, Phobos.
Yeah, I see it.
Hey, Phobos.
Emperor's asking, do you do physics? I'm learning about it. I'm better with math. Okay, so
Okay.
a rocket ship of proper length L leaves the Earth vertically at speed 4/5 c. A light signal sent vertically after which arrives at the rocket's tail at t equals 0, according to both rocket and Earth-based clocks. When does a signal reach the nose of the rocket, according to A, the rocket clocks, multiple clocks for some reason, and B, the Earth clocks?
Okay, let's think about it. First of all, which one should be bigger? Let's think about which answer should be bigger.
I assume the Earth is just kind of stationary in this problem.
And I got it wrong.
We're not worrying about like the rotation or anything like that. It's kind of weird to me that they happen both at t equals 0. It feels like a thing that wouldn't be simultaneous unless we're in some like the exact right frame to see it at the same time.
Simultaneous is a statement about two events. There, they're defining one event. They're
Oh,
saying the light arrives at the rocket's tail. That's one event, and it's just saying the Earth clock and the rocket clock both set their clocks to start to equal 0 at that single event. So the relativity of simultaneity doesn't really factor in here because we're talking about a single event.
oh, I guess we're both like we're okay. I guess we could both set our clocks to that event, and then I guess like a stopwatch, like you'd hit start right as the light gets the rocket's tail, and then you would measure different times after that.
Yeah.
Okay,
Yeah.
that's helpful. Hey,
I'm
Yash.
going to say the answer to A should be less than the answer for B.
Maybe. I think part A is pretty simple. It's in the rocket system.
The speed of light.
Would it just be L over C? Length over C?
Yeah, I think so. Yeah. Because in the rocket frame, it sees its own proper length of L. And speed of light
Yeah.
is invariant, so he sees light going speed C, so L over C for A.
Yes, someone on Earth sees the rocket running away from the light, so it's going to take longer. But someone on the rocket doesn't feel like they're running away. That's how I kind of have been thinking about it.
Part B is a little trickier. Let's see, part B, length of the rocket is L over gamma, right? Oh, well, we're going to need gamma here. Let's do gamma.
1/5 C minus C is 1/5 C. Wouldn't it be 5L? 5L over C? It's not going to be that easy, is it? No.
So I think gamma is 5/3 here, so it's 3/5 L. It's the length of the rocket in the Earth frame. Actually, maybe I'll call it L prime. That's probably a more sensible name.
It would look shorter. Someone on Earth.
Okay, so from the Earth frame, we have the lights here. At T, and this is going how fast? 4/5 C. This is T equals 0. I guess let's use prime for the Earth. So we'll call this T prime is 0. And then T prime equals the time we're looking for. Let's call it big T. Well, actually, we can just compute. I don't have to look at files out again. So that gap was closing at a speed of 1/5 C. So T equals first 3/5 L over 1/5 C. Like the gap is closing at the gap between.
So it's 3 times as much.
I think so. Is that consistent? Yeah. So you can't. This would be a useful question for you to answer. Why can't you just use the time dilation formula? Because the time dilation formula would say it'd be 5/3 as much, right? Time. So we get a different answer. We get even larger, 3 times as much, 9/3. So why is this not equal to? Can you see why? So these are our answers, right?
It's
It feels like both of those individually have some factor of gamma involved there, but I'm still. Actually, no, they would have.
Oh,
No, never mind.
the 1/5 became from 4/5 or 1 minus 4/5.
Yeah, yeah, you're right. Never mind. Thank you, color cone. That is weird. Why aren't those two things equal?
Well, I can tell you the blue one's correct and the red one is wrong. But this would be an instructive exercise to see why you can't just apply the time dilation here.
Oh, is it? Well, no.
Is my gum chewing going through? Are you hearing my gum?
No.
No.
Okay, good.
Discord is putting in a lot of work. Cutting out the Starbucks noise, the gum chewing.
Yeah. But you can't even hear the Starbucks background music right now?
No.
No.
That's
I've
amazing.
occasionally
They're
heard
playing
someone
something
like
really
talking super loud, but that's like briefly.
Sorry. Yeah, that was right next to me.
Yeah, that doesn't. It's not. It's nothing bad. Wouldn't time dilation apply? It's so weird.
Yeah, this is something we got to work out. So, because I've always looked at the Lorentz contraction versus the time dilation as kind of two different ways to do the same thing.
They are.
They are? Okay.
They are. But we didn't really use just the Lorentz contraction either. We had to use the speed, a different speed. Okay, so
Yeah.
I'm not sure if I should ruin this. Should I tell you the answer, or do you want to puzzle over this disagreement between the blue and the red a little longer?
Is there a good hint you could give us?
Yeah, maybe. The time dilation formula is a special case of the general Lorentz transformation.
So is time dilation, is that either going, let me think, or is that where your is that where your world line is vertical, parallel to the time axis? Or is it more general than that?
No, you're right. I think that yeah, so that's on the right track, I would say. Okay, I'll give you another hint. When you multiply by gamma to do time dilation between a delta t and one frame to a frame moving relative to it, you're assuming something about the two events in the first frame. That's not true here.
Oh, that
Like,
they occur at the same place?
yes, exactly. And so see, even in part A, the rocket frame, one event is the light leaves the bottom. Event
Yeah,
two is that the
yeah,
light hits the top. They happen in
yeah.
different places in the rocket frame even. So you can't apply time dilation because you get an extra amount of time going. We got bigger number, 3 is greater than 5/3, because that spatial distance in the rocket turned into an extra time distance for the Earth observer. So you could
Hmm.
use the general Lorentz transformation. Yeah, actually, let's do it. Do you know it? Can you tell me what's the Lorentz transformation for delta t prime? You can use that, and we'll see if we get the same thing. 3 over LC.
I'm bringing it in.
Is it like gamma delta x plus g over c delta t or something? Oh no, shoot. Okay, so unprime is the rocket. So we'll do here. So gamma's 5/3. Yeah. So if you just use the time dilation, you'll miss this term because the delta x is non-zero. If delta x is 0, the distance between the two events in the unprimed frame is 0. Then you do get naive time dilation. But here there's extra. They're happening at two different places. Although I think we need a plus here actually because we're going the other way. There's a whether you're going from prime to unprime. We're hyperbolically rotating one way, not the other. So delta t was L over C. And then V over C was 4/5. Delta X was L, right? I think it's C squared. So hopefully this gives me the right thing. 5/3, 1 plus 4/5 L over C.
Three.
Oh,
Yeah.
yes, that is 3. Good. Okay, so you can see clearly here what was missing was you can't use time dilation because they're happening at different places in the initial frame. So you have to use the full Lorentz transformation. For a simple problem like this, I prefer just to work things out like we did in green, but if you want to just pound some formula. Oh, my bad. Yeah.
So the essential thing is that it changed in space, not just in time, and so we need that extra factor there.
I don't like the language "it" because that implies there's one thing. You really need to think about events. There's 2 events. Light leaves the bottom of the rocket, light hits the top of the rocket. And the key here is that those 2 events have a time separation, but also even a distance separation.
Okay.
So you had the right idea, Don, but the language "it" I think is misleading because that implies one thing. There's 2 events here, so you need to always frame it in terms of events.
Okay. Fair enough.
That was a good question.
Yeah. Bringing number 3 below here.
Oh gosh,
This one seemed weird.
So if we were to have drawn a space-time diagram for question 2,
Oh.
Would we have just drawn? I'm trying to think of what we have 2 events, and the 2 events are spatially separated and have a time separation. So then,
right. So you can't just naively apply the length contraction formula. Yeah, that's a good point.
okay.
So here they're just naively applying the length contraction formula, but they're missing something about the doors. They're spatially separated.
Okay, now can we think of that in terms of Pythagorean identity? Can we say like the length contraction plus the time dilation or something? Is there a way to think of it like that? Like a horizontal side of a triangle plus a vertical side of a triangle?
I don't think so, if I'm understanding your question correctly. Because with these hyperbolic triangles, usually one leg is either t or the delta x axis. So, have either of you seen this paradox before? The barn pole paradox?
No.
No, I showed this I was talking to one of my colleagues at work last week, and he said he saw the book I was reading. He said, "Oh, are there questions at the end of the chapter?" And I flipped to it, this page, and he saw this picture of the person running through the barn, and he said, "Oh, I've seen that problem before." And I said, "What? You've seen this before?" I guess maybe it's a common question.
Yeah, I mean, there's a Wikipedia article on this. It's called the barn
Oh,
pole
does it really?
paradox.
Okay.
Yeah.
Yeah, I'd never seen this one before.
But so do you appreciate the paradox though?
I haven't read it yet.
Let me read the question again. I gotta remember what it's saying. It's like two different ways of looking at it. In one way, they can fit the pole inside the barn, and in the other way, they can't, maybe?
Yeah.
Is that what it is? Let's read it. Just at the instant the head of the pole reaches the closed rear door, the front door can be closed.
The doors probably open at different times in the runner's frame? It's the only way I can imagine this would work.
Oh, I like this. It says explain quantitatively and by means of space-time diagrams. Nice. So our two events. So our first event is that the head of the pole reaches the closed rear door. That could be one event. And the other event is what? Closing the front door? Okay.
Yeah.
Well, let me think.
It's in the lab frame, as one door closes, the other one opens at the same time.
Okay.
It sounds like.
They're simultaneous in the lab frame then.
Yeah, two doors shut and for an instant keep this pole inside the barn. Yeah, in this frame they're shutting that simultaneously. So that's what it means to close it in the barn.
Would it be helpful to figure out the velocity of the runner?
Well, just qualitatively, can we explain this? What is seen in the runner's frame? The runner's carrying their 20-meter long pole. And there's this 5-meter barn. Do they see their 20-meter pole shut up in this barn for a second?
No, the door's the door the rear door has to stay open for a lot longer, and then the front door will close later.
Oh, it's something like that, is it?
Well, I don't think it has to do
yeah,
with how long the doors are closed or open, because you could imagine them like it's more about at what time they close. So they happen simultaneously in this laboratory frame, but they're spatially separated. So if I hyperbolically rotate, that spatial separation turns into a time separation for the runner.
Okay. Yeah.
Partially. So the runner doesn't see the doors close at the same time. It's like the front door opens, then the back door opens, then the pole goes all the way past the back door, then the back door closes, and then the pole goes completely out of the barn, and the front door closes. Something like that.
Hey, Phobos got 3L over C. Nice.
Yeah. Oh, I swear, there's a typo here. Trough or through?
Trough, huh? Funny.
It is a barn.
So do we want to call the lab unprimed and the runner primed? Oh,
sure.
Yeah, yeah.
Okay. Excalibur's making me look like I write like a 5-year-old. I promise I don't normally.
We might need to transfer it to a new one because it's starting to die with all the stuff we've drawn on it. If it gets too bad, just let us know.
Okay, and I think we should draw the barn doors. So we put 1 at x equals 0. So let's call this the left barn door. That the right.
Do you have your lefts and rights reversed?
Well, I want to call it left because it's the
you're drawing it on the left.
Pole goes through first. Yeah.
Oh, okay.
And it's exactly 10 meters in this frame. So let's think about this.
Yeah, we could work out theta, couldn't we? If we wanted to. A hyperbolic
This-
angle.
The necessary speed. Yeah. You want gamma to be a half, right? Or sorry, gamma equal 2.
It's one of those two. I haven't worked out which one yet, but
Okay. So the pole looks something like this. Let's see. Hold up. Hold up. I'm getting kind of confused. Yeah.
so I guess in the left frame, like we would draw points on each of these lines. In T, they'd be in the same height for their opening and closing. I see you're doing these primed axes now too.
So in the lab frame, this pole is length contracted, so it barely fits in the barn. And this translates like, so this would be the left, this would be the back of the pole. This is the back. And then I need to draw the front of the pole, which goes through this point. So it'll be something like this. Oh, that's not parallel. That's also not parallel. That's about as good as I'm gonna do. That's the front of the pole. Okay, you can see, yeah. So this is these are the two events that are, oh sorry, let me think here. Wait, no, this is wrong. This is wrong.
Which part's wrong?
Um yeah. Sorry, I'm confused. Okay, yeah, so I think that the orange part, fitting the pole that way, that's what the pole looks like to the runner. But what happens when this pole goes through? Trying to figure out how to reverse here. Is there a highlight tool here?
There's like the background colors, I think, that are like transparent. No, apparently not.
Okay, like what happens is like when a one-dimensional object, sorry, like when a point goes through space-time, it traces out a world line. But when a one-dimensional object like this pole goes through space-time, it traces out like a sheeted area. So like this is the space-time existence of the pole. Okay.
Yeah.
And what's happening is the unprimed lab guy is seeing it in these slices. So he sees it shorter because the prime guy who's carrying the pole sees it in these slices.
The prime guy would
So let me,
see the left and right blue lines that you drew at different places, though, right?
I just want to redraw this better so it barely fits. That's the right door. Okay, and so this is what's shut up in the barn in the frame of T, the unprimed, the lab frame. So the green, what do you want, strip? That's the space-time existence of this pole. And these vertical blue lines for modeling the doors as points are the space-time existence of the doors. So
Yeah.
this instant here, t equals 0, is when he closes the door. He gets this green thing as he sees it completely between the left and the right door. Okay. Okay. But we have to measure it this way if we use the constant time, instants of times are parallel to the x prime axis. So this is what. So this is when t prime less than 0. That's when the right door opens. See this event? It has a negative time in the lab frame. I'm sorry, in the runner's frame. That means the right door opens. How to think about this?
Are you talking about this event right here?
Yes. To measure its time in the prime frame, I have to draw a line parallel to the x prime axis. And
Yeah, I see
it's
that.
here.
Oh,
That's fine.
okay.
Right. And that instant, the stick looks like this. Right? Well, so it's long. Well, I might have drawn this backwards. That might be the left door because he has to go through the left door first. Or that's the right door. Oh no, I did it right. I did it right. Okay. This event, okay, I need to label these events clearly. This event is L closes. And let's imagine their default state is open. So they close for an instant and then they reopen instantaneously. All I need to talk about is when they close. So this event is when the left door closes and the right door closes. And those happen simultaneously in the unprimed lab frame because the poles instantaneously in my bar and I go, and I close out for like a instant and then I unclose. I open the doors, unclose.
Okay.
I open it. Okay. All right. So now what does the runner carrying the stick see? They see I'm running. The right door closes and opens right when the front stick gets to it. That's fine. And then so I can still clear it, right? I still go through the right door but the left door is open here. At this social time, L is open because its default state is open. We agreed. And then the next relevant moment is here. Just colors are getting all screwy. Maybe I should erase that. But here, R is open. So these two events, the black circles, L closing or R closing, they're not simultaneous in the runner's frame who's carrying the stick. And even more importantly, they close right after the relevant part of the stick gets to the door. So if you imagine, oh, I circled the wrong one here. I'm so sorry. And I did it on the other side too. Wait. Oh, I know. I was trying to say something different. Okay. Maybe it was okay. Yeah. Okay. So if we're looking at this in the green frame with the stick translating, I'm drawing it orange. It's going up and up and up. And when it gets, and the doors are by default open. And then when the stick gets to the right door, the stick is partially out of the barn through the back. That's what this section here is. You see, that's okay. The left door is open. And so it's open. It gets to the front door. Actually, I can draw some pictures. Well, that's what happens first. Let's just close. Then next, when the left door closes, That's that black event there. That's okay. The stick is sticking out of the right door, but that's okay. That's open now. Well, let's do. So this is kind of what it looks like in their frame. The stick is moving to the right. Sorry, I'm not explaining this very well.
So you're saying from the runner's point of view, there is no, they never actually see the whole thing inside the barn.
No, I mean the barn is shorter in their frame. The pole is 20 meters long, and the
Yeah.
barn is 5 meters
So
long.
right, so it's no way. There's no way.
There's no way. In the way that's resolved is that the doors are opening non-simultaneously. It's like closing non-simultaneously. They're default opens. So
Okay.
the right door closes for an instant, right when the stick is about to hit it, and then it opens again.
Yep.
And at that moment in time, moment one, part of the left stick, 15 meters of it are hanging outside of the left. That's fine. That left door's open. And then right when the stick clears the left door, it closes, but you've cleared it, and the right door is now open, so the stick is hanging out of the right. So actually, to draw this more to scale, it'd be something like this.
Yeah.
Because there's 15 meters hanging out.
You know what would help me to see? I can see where the 10 meters is showing up on this first diagram, but I don't know where the 20. Let's see, the 20 should be the diagonal distance, shouldn't it?
Yeah,
The-
this like
the-
orange line. That's the,
Yeah, that orange line's the 20. So where's the 5?
that's the.
Does that show up somewhere? Is that the
Yeah, that's the length between the two blues as measured by. Uh, that should be this distance here.
Also, shouldn't
That's
the
a
orange line be a lot longer then?
Yes.
Yeah, it's okay because we only have like so much room on a scale draw, but just like so I can like visualize it. Yeah.
I didn't know where this was going when I was making it. But qualitatively, it's correct.
Okay, and yeah, if it was to scale, the orange line would be like 3 times as long or something. But okay, I think I'm more on board with this space-time diagram now than knowing that.
I'm trying to draw a triangle, but I think it's wrong. How does this work? Because there's no way these 3 numbers work. Yeah, this is wrong. I think 2 of them were right.
Well, okay, you can think of it this way. Well, let's see. Uh, two. So I think this is delta x. I may be flipping the primes here.
Oh,
Is this the one I'm looking?
sorry.
Maybe not.
Patient, you just committed to UCSB for applied math as a junior transfer. Congratulations. Welcome to the applied math side. Sorry, patient was just in chat the other day trying to decide between pure and applied math.
Sorry, that's my wrote there as well.
Trying to do any sort of triangle here feels dangerous when we're measuring distances the way that we are.
Oh, it seems like it should be.
What are you trying to get at with your triangle pen blocks?
I'm trying to make my head understand. That's all. I don't know. I don't know if the triangle's helpful.
Okay.
I don't know if the
Yeah, I'm
triangle's
not
helpful.
sure it is helpful,
Yeah.
but I want to get it.
So you're saying
Yeah.
that so in the runner's frame, the pole is 20 meters long, and the barn doors are only 5 meters apart, right? That's what they said. So in your two lower pictures, the space between the L and the R is the 5 meters, and then there's 15 meters hanging out in each 15 meters of the pole hanging out of the barn at each
What
event,
about
right? At each time.
we're talking about the green frame?
Oh, green.
Yeah, for like this is
The bottom
the
two.
runner's frame where you
Yeah, but you have to measure it
two
in the
separate
green
things.
frame, the runner's frame.
That's what
right?
I'm thinking. Yeah, in the green frame. Yeah, gotcha. Yep.
Yeah, so that's this overhang I circled on black here. That should be 15
Yeah.
meters. 'Cause that's
Yeah,
how much. Yeah, that's the 20 meters of the orange pole minus the 5 meters of the blue, which it looks a lot longer than that. So yeah,
Oh,
and then this is the overhang. Yeah, so that's this overhang,
wait
and
a
that's
second.
that's
Okay, wait a second. I think I understand something here. So my picture's wrong because this is the 5 here. The 5 is how much is inside the barn. Is that right? And there's a 15 hanging off down here.
yeah. The barn is 5 meters big in this frame, so it has to be yeah.
Oh, that makes more sense, doesn't it? Because this is like the non-Euclidean metric where the hypotenuse of the triangle is supposed to be shorter.
Mm-hmm.
Okay.
Oh, are you drawing? Which triangle are you drawing from my picture? The
Oh, I don't know. I'm trying to draw
I see.
this 15 is the part you circled. This 15 is the part you circled.
I see. So the triangle is this triangle.
Oh, okay. It's like
The triangle I drew
there,
is this
yeah.
triangle underneath the
Yeah, I see. Yeah. Then you're exactly right. And this vertical distance is the negative t prime I have here. That's this.
yeah.
Because that's wait, no, that's not quite right. I'm sorry.
Oh.
That's
Yeah, and that vertical distance is the amount of time between the stopwatch for the two events, right, on the runner's wrist. Is that what you're saying? Between the first front door opening and the back door opening?
which
Closing?
say again. Sorry. Say again.
That last that one you just drew the arrow to here. This
think
side
that
of
was wrong. Yeah, that side. Okay.
I'm thinking of it as the amount of time that would pass on the runner's wristwatch between
No,
the
I don't think
two.
so.
Oh, it's
No,
not?
because
Okay.
I don't think so. How do I get that? Oh, here. You saw this distance.
Regular delta t, right?
Yeah.
Not t prime.
Yes. Yeah. So that's the lab time for all this left door, right? This is the left door.
Oh, you're right. It's the lab time. It's not the runner's time.
So this is when the left door closes for the runner. So this here represents the time for the runner between when they first see the right door close and the back end of their stick clears the left door. So right door closes, I clear the left door. This distance here is that time for the runner, and it's non-zero.
Yeah.
This closes at a different time than this. So this is how much the spatial distance, the 10 meters between the front and left door, turns into a time difference for the runner. And that time difference is what gives this longer pole the ability to clear the barn, as shown in my pictures below.
And
Yeah, so
now
the key
we have
here is
enough information to find that time, don't we?
I'd love
We
to
could
get
find it
delta
if
t
we wanted
prime.
to.
Yeah.
yeah. Actually, so we could do it. Yeah, how do you want to do it?
Well, I worked out gamma a second ago. Oh
It's
wait,
2.
I worked out
Gamma's,
that, I worked out, yeah, gamma's 2, so the velocity I got was √3/2 times speed of light. That's the runner's velocity, I think. I think that's what it works out to, √3/2, so like 86, she's running about 87% of the speed of light. Does that feel right? Yeah, you're working it out. Yeah, let's see. Oops, what am I doing?
√3/2, is that what you got?
Yeah, √3/2.
Yeah, okay. Yeah, yeah, you said that's 86, is that right? Is that what you said?
Yeah, 0.866.
Yeah, that feels right. Okay, I wonder if we can do this like from the picture instead of formulae.
Yeah, that'd be great.
So we're trying to find the time between the doors closing. So that would be this. I don't know colors, but this time. So there. Yeah, I think it'd be more pedagogical just in the picture. That's also harder. I mean, the proper thing is Lorentz transformation. So let's go back to Don pasted it.
Oh,
Look at that
up above
again.
in the problem. Yeah. I'll just copy paste it down.
Okay. Yeah, I was trying to figure out how to do that while I was failing. Okay. Okay, I want. I'm gonna do plus again because I think
Oh, we do have
depends on the
a
sign.
delta t formula. Actually, no. Never mind. I thought we had a formula that was kind of like cut out a lot of the calculations for delta t and delta
Probably
t prime.
because one of these terms is going to be 0. So that's I'm putting in v there.
Oh, that's the integral.
And the distance is L. V squared. Okay, and they're simultaneous in the lab frame. So what's happening here? Oh, that's stupid. That should be a C. I'm still getting it. Oh, I should get over C. That makes sense. Okay.
L is lab frame distance, so 10?
Right. Yeah.
Okay.
So I think that's the non-simultaneous, the duration between the doors closing that's introduced in the runner's frame. So is it 10 meter bar you said?
Yeah, the runner sees 5.
Um,
The lab sees 10.
So
I can Wolfram alpha that.
yeah, it's good to try to get hand approximations. Let's see how close I can get. How should I do this? 0.86 over √3. Oh gosh, I don't know √3 that well.
1.6, I think.
1.7.
Or 7 maybe.
1.7. Oh, so this is about a half, a little bigger than a half. Let's say it's 0.6 times 10 minus 7. So that's about 60 nanoseconds. Is that right?
Wolfram says 5. They give it times 10 to the 8th, and I'm getting confused with powers of 10, but that 5.7 times 10 to the minus 8,
so
so I think that's okay.
I'm off by 3 nanoseconds. Forgive me.
So that's still like pretty quick, but not exactly simultaneous.
But that's enough time because
So
she's
that's how
moving very
much time
fast,
she had to get that 15 meters, squeeze it through the barn. Okay.
Well, let's see.
Yeah.
That's the amount of time between the two pictures I drew.
Yeah.
Yeah, you're right. Yeah, but in her frame, the barn is moving towards her at this 86% speed of light. So
Okay.
even though it's in her frame, it's not a very long time to get the pole through, but the barn is rushing towards her extremely quickly.
Yeah.
So actually multiply this by that speed. So let's multiply that by √3 over 2c. That's what we said it should be. So what did that give, Don?
√3 over 2c? Or
times that time.
5.7 times 10 minus 8 times square root 3
So that's how fast the barn is coming towards her in her frame.
over 2 times speed of light.
Yeah, so actually is there a lasso tool here? Things?
You can draw boxes. I don't think there's a lasso.
Because I realize my picture is bad. It looks like I'm drawing the two sequence pictures. It looks like I'm trying to draw the runner's frame, but I kept the barn in the same place, so it's misleading.
It's getting 14.8 meters per second. That seems kind of... Shouldn't it be way higher?
It should be about 15.
Oh, okay.
She's got to clear that 15 meters through.
Oh, right. Yeah. Okay. So that... Maybe if I put on some more decimals, it'd be closer to 15.
What was the number you said?
Okay. I wrote it that the more sevens I put on, the closer it gets to 15. So I was gonna call like 14.99.
Let's see. Before we plug in numbers, let's see this. We can do this times √3 over 2c. Or I guess we want this one. So that's 3 halves L over L. And L was 10, so it is exactly 15 meters. Yeah, good. Yeah, so we didn't have to, yeah, I should have done, we should just use this expression. So L is 10, right?
Yeah.
So it's exactly 15.
Yeah, L is 10, yeah.
And that's what exactly clearing these things. Okay, it's all good. I think we beat this pretty good. We got.
Yeah, I feel like we pretty thoroughly answered that one. Sorry, what was that?
So do you want to crush another one?
Yeah, I mean, the number 4, I mean, I don't know. It doesn't seem too long. We're nearly at the 2-hour mark, like just a few minutes, but I don't mind going for another one.
Sure.
Okay, I'll bring it in down below again.
I'm not like robbing you of the doing this yourself, struggling through this yourself, am I?
I've been able to follow along, so I mean, maybe this one like will let us like try and start it and see if we get stuck.
Okay.
Maybe a little hard to find. I kind of put it out on the. It's like down and to the left of the 2 barn door pictures.
Can you like enlarge it?
Oh yeah.
Can I do that? I was trying to.
You can do it too with number 1, like the little pointer or cursor tool.
Oh, it's doing the hand. Got.
No, the hand is with hand. Okay. Satellite orbits the Earth in the same direction it rotates in a circular orbit above the equator, distance of 200 kilometers from the surface. How many seconds per day will a clock on such a satellite run slow compared to a clock on the Earth? I remember reading this one last night, and my immediate question was, is it stationary above the Earth? I assume it kind of has to be for us to be able to make progress on these calculations. Well, like presumably as the Earth, like if the Earth rotates around that direction, the satellite would need to be always above the same spot. It's kind of looks like the golden snitch that I'm drawing, but that's a satellite. Hey, Nikhil. That orbits the Earth in the same direction. And so assuming it does stay in the same spot above the Earth, I guess the speed of the satellite is going, the distance is 2 pi times the radius, which is the radius of the Earth, plus 200 kilometers. Well, maybe we want that in meters.
Radius of the Earth, 6,378 kilometers.
Okay. I mean, I don't mind just keeping it as like the big R, but
So if we add 200, we got 6,578 kilometers.
And then that's a full rotation, so we need a day in seconds. Ugh, that's Wolfram Alpha.
2,600 times 24.
86,400. Actually, if the satellite does stay above the same point in the Earth, the satellite doesn't look like it's moving relative to the Earth. Wouldn't there not be a time dilation between those two observers then?
Well, we could find the velocity of the, maybe we could find the velocity of both points, like a point on the surface of the Earth
Oh, true.
and the satellite, both going in circles.
Yeah, the satellite is going faster even if it's stationary. Okay. How do you spell satellite? Oh, they spell satellite right there. I'm just going to say Earth, but this is a point on the surface of the Earth. And so I guess we can just care about the difference. And actually, yeah, I guess the radius of the Earth is going to drop out anyway. If we subtract them. Okay, well, I guess we'll see if we get a similar result. I'm not sure. Seconds per day.
Oh, we didn't even need the radius of the Earth. Yeah.
Yeah. So can we just go for the time dilation formula now? Like we just get gamma.
Yeah, that's your. Yeah, couldn't you just plug that in, put that over C and square it? 1 minus that.
guess I'll go to Wolfram Alpha for that.
So
Mhm.
does this say somewhere it's staying above the same point? Or I guess we assume that from the satellite.
I was
where,
assuming that.
like
That's what I was assuming too, because it said it
It would
orbits
be
in
more
the same direction
information,
it
right?
rotates.
yeah, but like it could be going slower, right? A slower angular speed and losing ground on the Earth, or I guess that should be assumed.
Like, I assume we need more information about like how it gets the speed differences, and they don't really say that.
Yeah, no, I think it's a safe assumption. I just don't like the wording.
Me neither.
I got 14.54 for that delta V.
14.54. Okay. Let me write that down.
Wait a
14
second.
point-
14 meters per second?
I guess it's per second. Maybe that's reasonable. I can calculate that too. 1, 2, 3.
So like the picture I drew is what you're assuming. Like the satellite's always above the
I
same
get the
point.
same.
P.
Yeah.
Yeah, okay. Yeah, so it has to be moving faster. Yeah, okay.
And so what are we actually trying to... right now with Gamma, I'm getting confused. I guess we want 1 over root that. Is that what we always do for Gamma?
Yeah, I'm looking at equation 415.
Squared over... Is that... I'm getting basically 1, like slightly more than 1. Is that... I guess it should be more than 1. That's like barely. There's like tens, like it's literally 1 point and then like 10 zeros.
I mean, I think this is reasonable.
Oh, it shouldn't be that big of a difference, I guess. Maybe.
Yeah, although we would have, well, I guess we did satellites after relativity, but still, yeah, I think it should be modest.
Okay. And so if a day on Earth is 86,400 seconds, we're going to take the number we just got, that's slightly more than 1, and multiply the length of a day by that. And that's our new, or that's like the discrepancy. Or that, no, that's the time the satellite measures that we would then subtract off to find the discrepancy. Minus 86. Oh, you know, they did a similar calculation in an example, and they did get something that's like 10 to the minus 8 or something. So I'm getting a difference.
Yeah, that's right, they did.
Okay, if I do gamma times 86,400 and subtract the length of a day as measured on Earth, that difference comes out to be 1.02 times 10 to the minus 10 seconds, which is maybe reasonable. I see you're working now.
Yeah, the example in the book was about 3 times 10 to the minus 7 seconds.
Okay. And I think they were just doing there's maybe a different scenario, so it's maybe okay, or hopefully it's okay that we got a different order of magnitude. I see it. They have they're completing an orbit in 12 hours in that example, which they didn't give us here. All right, see ya, MMD.
But you have the solutions though, don't you?
Oh yeah,
You can just
if you want, I
compare
can
with
check it. I was
this,
just waiting for you to. If you want, I can just check
Oh, I
it.
gave up.
Oh, okay,
I got
okay.
to the point where I actually had to put in numbers, and I gave up. I mean,
It just
I was doing
feels
it.
small.
Yeah. I mean, I think it should be small. I mean, what would you expect? Like a minute or something? 60 seconds?
Oh, look at that picture you just went by. Yeah, that's what Dr. Cook
Oh.
had.
Oh yeah. That's the same space
Is it?
time for the pull problem.
Yeah, it looks similar. Yeah.
Hot dog.
The speed of the satellite's radius distance RS from the Earth's center. Oh, they're doing something weird here.
Oh, we had to find the speed of the satellite using
So was the assumption
energy.
that we made bad, or like how are we? Oh, they're equating accelerations. Angular acceleration equal to gravitational acceleration.
What?
I don't know why they're doing this, but they're taking velocity of the satellite squared over the radius of the orbit equals to g mass of the Earth. I mean, I'll just put a screenshot in the Algebra so you can see it. It's probably hard when you're on the iPad.
Oh,
That's the
no,
first
I
part
think
of the
this is what I
solution.
said at the beginning. I think this is what I said. The assumption that the satellite's staying over the same point is wrong. So I think what they're computing. Yeah, they're computing how fast the satellite must be moving by its gravitational attraction to the Earth, which is reasonable. So it's not, the speed is not good. Is the condition to find the speed of the satellite is not it rotates at the same angular velocity as the Earth. That's equivalent to staying above the same point P. That's not it. You have to get the speed of the satellite. The circular orbit, mv squared over r is equal to its center directed force, gravity. So it's not going to. So okay, my question at the beginning was good. I was like, "Are we sure we should do this?" And I just went along with it because it didn't say it in the question.
But we don't have any more information. How do you know this doesn't make any sense to me?
Because the speed of the satellite is given by its gravitational attraction. The gravitational attraction implies a centripetal force for it to undertake its circular orbit.
But you can be 200 kilometers away from the Earth and moving at all sorts of velocities. Like I feel like
if it's going too fast, it'll shoot off into space. And if it's going too slow, it'll fall in and crash. You know, there is an exact speed it has to maintain to stay a certain distance from the center of the Earth. Oh man, I should have thought of that. I've seen that before. I didn't even think of that.
When you rotate a ball on a string, the tension is providing the centripetal acceleration. So for a fixed tension,
force,
for a fixed tension, it has to be going only one particular speed. Yeah. Okay. So yeah, the beginning assumption here that the satellite stays above the same point of the Earth is wrong. So it just found the speed in a different way, which is good.
So once they found the velocity, we would have been good after that point, right?
Yeah. 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 Well, actually, and it's interesting. You weren't that far off. No, I guess no. I'm sorry. I guess you were. It's 29 microseconds. That's like 10 to the 5-ish. Yeah, it was okay. It's off by 5 powers of 10. 5 powers. That's not great.
Oh well.
Annoying. I'm gonna redo this calculation, but
why did they say a satellite orbits the Earth in the same direction it rotates?
I think so. There's not
in the same direction it rotates. I got confused by the way it was worded a little bit. I think.
because if it was counter rotating, you'd have to add on to this V surface or V satellite. Like there'd be a larger difference speed, right? You'd have to.
Could be extra relative velocity.
Oh,
I think let's
They
see.
would add rather than subtract like we did, I guess.
oh, wait, in the same direction it rotates, that it means the Earth. A satellite orbits
Right.
the Earth in the same direction the Earth rotates. Oh, I was thinking it meant in the direction the satellite was rotating. Okay, all right.
Oh,
That's where I was
Satellite's
confused.
effectively a point particle here.
I thought they meant the satellite was rotating so it could keep its face, its components pointing down towards the surface all the time or something.
No, that was the wrong first step
Yeah.
in what we did.
Yep. Yeah,
wow.
sorry, Don. I should have thought about that because I've seen in dynamics, I've seen problems like this with what do they call it? There's formulas you can work out for a given height. You know the velocity. It doesn't matter what the mass is. For a given height above the Earth, you have a certain transverse velocity. You can work it out as a function of height. If you want the
stay in
thing
a
to
circular
be in
orbit.
orbit, to stay in orbit, yeah.
But this is
And I
simple
knew
because
that.
it's a circular orbit, so it can use some triple accelerate. If you want a elliptical orbit, then yeah, you have to like use Kepler's law and stuff. But yeah, this is not bad. Yeah, because I was reading the problem, I was like, where does it say that it's like?
I just don't know what else it could be. I don't know. I don't know enough about orbital mechanics. I'd honestly love to learn about it at some point in my life, but it's weird to me that they wouldn't have the same angle. Sorry, what?
There's a name for this when it happens, like when a planet is orbiting a star and one face is always facing the sun. There's a name for this, like phase lock or something.
Yeah.
If I'm forgetting the name. I mean, I guess I don't really know satellites very well, but it seemed like a reasonable assumption because I thought maybe the satellite wants to be transmitting to the same spots or something. But yeah, no,
I mean,
its velocity is fixed by centripetal force provided by the gravitation of the Earth. That's it.
Yeah, makes sense. Makes sense.
for circular orbit though, I feel like the perfect velocity should just be the. I'm gonna be stuck on that, I guess. Well, tidally locked? Maybe, yeah. Okay, I guess we are pretty well past the 2-hour mark now. We'll definitely
great
meet
today.
more in chapter 4. Yeah.
I gotta head up to. Yeah. Okay. Is it chapter 4?
Yeah. So we should
Yep.
spend at least one more week on this.
Can you
sure.
pull up the table of contents? Our Twitch is
Uh,
showing an ad right now. Sorry, but I just want to see. I want to see when the GR really starts.
I think we have one more chapter after this, and then at least there's like a part 2 of the book where it seems like it's going to start in chapter 6.
Okay, I'm just getting out of the ad.
Okay. So I'm showing chapter 5, the next one, and onward.
Yeah, even 6 is kind of introductory. I think 7 is where like I would say the real meat and potatoes begin. But 5 is good too. I mean, you'll learn a lot in 5. Like that's just kind of doing special relativity even more formally.
Nice.
Okay.
Yeah, 7's got some fun stuff, like this warp drive. I think that'll be a lot of fun. And so yeah, like I think 7 is when you're going to get an introduction to the metric, like in general, and that's like a new mathematical object. I remember it took me a while to kind of grok that. So like, yeah, the metric is usually the main mathematical object you're playing around with when you do GR, and it seems like that's when you're really going to see it is in 7.
So it seems like most of this reading group is going to be spent on like the prerequisites.
Well, I mean,
Depending how far
so
we
you
can
wanted to
go, I
go to
guess.
chapter 9.
That's what I've been.
Your goals.
Yeah, I mean, I think we should definitely be able to get through chapter 9 at least in the time that we have.
Can you show me the Can you scroll down the table of contents so I can see the subsections in each chapter for the next group, the next page of the book? Yeah. So yeah, 9 is definitely essential. 10 and 11 can be skipped. I really think you should do 12 too.
It sounds cool. Is there one you think you were the follow? Yeah, I think we're at a pretty good pace right now for getting through the earlier chapters. So hopefully we can do more than just chapter 9. And so I guess we can like skip ahead to 12 once we do get there.
I mean, 9 is a pretty meaty chapter. Like, so I gave that 2-part talk at my university, and a big chunk of both talks was chapter 9 because that's basically like. Do you remember from mechanics where you solve for the orbit or the general orbit in Newtonian mechanics and you show us an ellipse? Have you done this calculation?
I don't think
I've
so.
seen it. I've seen it.
It's like you get this effective potential with the positive L squared over R term. Yeah,
Conservation of angular momentum, right? Is that part of it?
That's a big part of it. Yeah, I mean, it's a pretty involved calculation even in Newtonian mechanics. But chapter 9 is basically redoing that in general relativity, and it's way more complicated.
Nice.
Chapter 9 is a pretty meaty chapter.
When it's less than 20 pages, okay.
Well,
it's gonna be pretty dense, I guess.
Well, that section 9.3. Yeah, I mean, there's a lot of calculations he leaves in the homework. So,
okay.
Yeah, like, and the end of 9.3, calculating the perihelion shift or precession. Yeah, he's like, in this integral is this, and then you get this, and yeah, I mean, you might have a reading group where you do the whole problem solving is like one problem.
I think we did that with E&M too, so that.
Okay. All right.
I'm okay
I'm
with
gonna
that.
hop off here.
Sounds good.
This is fun.
Yeah, thanks for being here.
Thanks, Dr. Cook.
All right. See you guys next week.
See ya.
Yep.
Bye.
Are you gonna be out of here too, Fembox?
Yeah, let me get out of here. I've been waiting to pee for a couple minutes.
Sounds good.
Yep.
All right. Well, I'll
All
talk
right.
to you later.
Thanks.
Yeah, thank you.
Yep. Talk to you soon. Bye.
Bye. Nice. Another reading group in the bag? There's a better expression. I can't think of it though. Not in the barrel. Dr. Cook is on that chapter fascinating say Kruskal Sakaras. I'm probably saying that wrong. I can't wait to learn what that means. Okay, we'll do math for a little bit here. Just give me a minute to switch over titles and categories and YouTube thumbnails and all that sort of thing. There's that. Okay, Twitch is up to date. Let's get YouTube up to date. That. I always say I should get this on hockey, and I assume maybe I can't do it on hockey. I'm sure I'll keep on saying that and never actually do it. Okay. All that stuff is up to date now. Let me upload the image to Excalibur. Take the Excalibur image and put it on Discord. Complete opposite of the thing that I said. we might only need one more week because we got through a fair few problems. Sorry, I'm debating. Oops, not that. What am I doing? There. I'm debating how I should frame. I think we only need one more meeting on chapter 4. That's my gut. Because a 2-hour session, I think we can knock out quite a few problems. Yeah, this was a great discussion. I think we can make do with just one more meeting on chapter 4 because I feel like we'll be able to get through quite a few more problems next time, and then because like today we had less than an hour worth of problems and we still got through 3 of them. So if we do a full 2-hour session just on problems, I think we'll be able to get through the important stuff of chapter 4. So maybe I'm going to say we're going to do chapter 5 Saturday after next. So we got 2 weeks. It's more time than we have for chapter 4. One more time on chapter 4. Chapter 5 on the Saturday after next. And so yeah, as long as we can keep the general pace of about 2 weeks per chapter, we should be able to get through 9 and 12. I think I calculated that at one point. And we're saving time because chapters 1 and 2 we did at the same time. And chapter 3 we only spent 1 week on. So I'm hoping that we're actually going to be a little bit ahead. And we'll have time for more stuff. I definitely won't want to read that paper. Okay, close out of that. Was I gonna check something? I think I was gonna do something else, but now I can't remember. I don't know. I want to redo the calculation for number 4. I'm really annoyed that I didn't do it right. Look at Martin's. That's true, Fizzbuzz, yeah. Ugh. That'd be another good thing to do. It's like another group in the bag, but there's another one that I can't think of. Okay. So now we start by doing angular acceleration is equal to gravitational acceleration. That's the right way of starting this. These radii are not, they are the same. So as constant speed, acceleration must be directed towards the center of the Earth, central acceleration, so do F equals ma radially. Right, I'm cutting out the middleman of canceling the masses of the satellite. But yeah, I think that's where this comes from. A reading group in the hand is worth 2 in the bush. Yeah. You know, it is, yeah. A reading group that actually happens is much better than two reading groups that don't. So I guess we can solve this for VS. Now, I didn't fully read the answer on purpose. They were doing some weird stuff with dividing each side of this by C that I don't quite know why. What would I do here? What do I want to do? I think what I want to do is go back to what we were doing. I think the... No. Yes. We should get... We could plug in the constants. I think I'll keep them symbolic as long as I can, though. I think the velocity of a point on the Earth is still a helpful thing. Like, I still want to subtract, do satellite minus Earth. Um, 2 pi radius. And a day is 86,400 seconds. Dynes. I'm glad we're not worried too much about the units in this book, because I would have a hard time dealing with the Gaussian units like dynes and remembering to do centimeters instead of meters and stuff. Okay, this is getting annoying enough that we probably do want to start plugging stuff in to get this difference in velocity. Yeah, the small r is just big R plus 200. Or, 200,000. Well, actually, in centimeters, 20 million? Okay, so we got square root g, which Fembox is saying 6.67 times 10 to the minus 8. I'm not going to worry about the units. So times the mass of the Earth, 5.97, 10 to the 27, divided by the radius of the satellite, so Earth plus satellite. Maybe I'll just do 6. Oh, we do have to convert that, don't we? I agree with your conversion. Radius of the Earth. 200 kilometers in centimeters. No one judge me. Two times 10 to the 7. So should it be 6.58 then? Do I think about that right? Yeah, I think it's 6.58. Yeah. Times 10 to the 8. Okay, that's my square root g over r. Now we're going to do minus 2 pi radius of the Earth. which was that bad. No, we haven't done race either yet. 6.38 times 10 to the 8. And we're dividing by seconds in a day, 86,400. That's a big delta V. This is centimeters per second, though. So the meters would be a little bit smaller. Okay, so Papador is asking, do Taylor series work for higher dimensions? I feel like I've looked into that before. I don't remember what the answer was. Let me just write this one thing down so I don't lose my train of thought. It went all stretchy. Uh, 7.32, I'm calling it. I don't imagine Taylor series. I mean, maybe. You definitely could if you choose a particular direction. But that's basically making it a one variable again. I can talk about tangent planes being basically linear approximations, yeah. Oh, is this a paraboloid? Papadori, I guess the answer is yes. At least, I don't know if it's easily done for higher orders. But there is something there. Oh. Yeah, just use this formula right here. It's very easy. No, I can kind of see what's happening in this formula. It's not too different from the regular formula, I guess. You just get a bunch more terms because of all the partial derivatives. Does that link even fit? Yeah, it does. That's kind of shocking. Is it shocking? Maybe it's not shocking. I don't know. You're saying why your machine learning program works. Oh, does it use this? That's funny. Okay, 7.32 centimeters per second. Wait, I'm missing my order of magnitude, aren't I? Times 10 to the 5th. In meters per second, we'd reduce the exponent times 10 cubed. Yeah. That's just 730. No, that's 7,320. Okay, so let's work out gamma. 7 kilometers per second sounds okay. Okay. $73.20. $73.20. I'm gonna need the units. Over speed of light. Doing a bunch of partial differential calculations in your program. You had no idea where it came from. Oh yeah. Wolfram, this can't be right. It's too small for Wolfram. There we go. I wish we could convert that to scientific notation. 1, 2. Oh, that's why the book was doing the 1 plus a weird thing. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. I think it's about what the book got to, but I'm not going to check yet. Okay. So that's our gamma. And so now what we do is we measure a day as the satellite would measure it, which is gamma times Wait, is satellites? It made sense to me at the time, but now it's not making sense. Does a satellite measure a longer time or a shorter time than an observer on the Earth? I feel like it's longer. I'm having trouble saying why. An observer on the Earth would feel they're stationary. They would measure 86,400 seconds in a day. They would see the satellite moving around the Earth at the delta V speed that we found. Isn't it shorter? Now I want to divide by gamma. Freaking relativity. I don't know how I'm supposed to think about this. I'm going to say the satellite should measure a shorter time. So that clock runs slow. Okay, yeah, so it doesn't measure shorter time. Okay. So we're actually going to do a day as measured on the Earth. Is this the time? This time is satellite measures. I'm still getting caught up on the interpretation of this, I guess. But we can see what this number turns out to be. I can't copy paste this number. Oh, I can. One, two, three, four. Okay, yeah, so nano is 10 to the minus 6. So 25.7. Micro, yeah, okay. Micro makes more sense. Nano is 10 to minus 9. They say 29. But we might have done it correctly. We just rounded differently. Oh, they use an approximation? No, don't do that. I guess the book was written in like 2002. I don't think Wolfram Alpha was the thing then. But no, you had programs to do this. Come on. I mean, they're literally doing a Taylor series approximation in this step, it looks like. That I feel like we're more accurate than they are. Uh that's what my delta V is here. Why are they doing this? I don't get what the ratio of gammas is supposed to be. Oh wait. Oh no. Am I wrong? You can't add velocities like normal. Are they supposed to do this? Or no? No. No, wait. I think I'm okay. This is for velocities measured in different frames. right? Is it? Please tell me. And this isn't what they did either. I have no clue what any of this is down here, to be honest. I don't know what this quantity is supposed to be with the ratio of the rates. I can't tell. I don't know. My answer is pretty close. It's the right order of magnitude. It could just be a rounding thing. I think the addition of velocity string is not related. I say hope not. Yeah, the 3.4 is this. It's one. They're like dividing gammas. They never do delta V like I did. I don't get what this does though. Apparently this is. I don't know what that is. What's actually happening here? They're taking a day, 8.6 times 10 to the 4. They're multiplying it by the gamma obtained from the satellite's velocity and dividing it by the gamma obtained from the Earth's. Why is it surf? I don't know. It's like this is coming from a third frame or something. Oh, surface. Okay. Ugh. BJFR for an observer is not with respect to the center of the Earth in the inertial frame of the Earth. Okay, that's starting to click then. I think that's where I had just gotten kind of. It's like a third party who's just watching all that happen. It still is weirding me out, but thank you for saying that. I just briefly looked at the book that you linked, Benbox. I downloaded it. Let me pull it up. Oh, just okay, fair enough. But were they in a specific like part of the book? What the heck is happening here? Sum of 4. Okay. These drawings are kind of goofy, but oh, okay. Okay, so they don't say this explicitly, I don't think. But I think it makes sense where neither the satellite frame or the Earth frame is inertial. They're both rotating. And so you do need to get that third inertial frame involved somewhere, I guess. The first sentence? Rotating about. Okay, yeah. That's where they. Okay, fair. And so they take the length of a day. They divide out the Earth's gamma. Oh yeah, because okay, 86,400 is what the surface of the Earth is what an observable surface of the Earth measures. That's a shorter time than the inertial frame observer. So you divide that out. And now that you have the time in the inertial frame, you multiply by the satellite's gamma. Shouldn't the satellite also be divided? The satellite should also be measuring a shorter time than the inertial frame, right? Oh, wait. Am I thinking about this wrong? No, oh no, this is 1 over gamma. They are reducing it. Oh, okay, yeah, this is... This is a very weird way of... Or it probably makes sense, but this isn't... These are both 1 over gammas. Or rather, this is just gamma. That's 1 over gamma. So they are both being divided. It just looks weird how they presented it here. Okay, 4.4. I don't think I... This one, yeah, I had a hard time working out why this one was the way that it was. Relativity is hard, as it turns out. I don't want to go for a ton longer here because my voice is already starting to feel, and I've been kind of pushing my voice this week. But we can do like we can go for a little bit more. What do we want to do though? Like I could pull linear algebra. I just learned some new things, so we can go on to a new chapter. Maybe let's do that. I just learned about positive definite matrices, and it was kind of sick. Wait, what? Where are they talking about in this book? Oh, here. How much slower the satellite clock is than the Earth's clock. The numerator tells you how much slower the satellite clock is than the Earth's clock. Thermometer. Hey, Central. It's good to see you streaming again. Timer tells you how much slower this Earth's clock is than the Earth's clock. Glad to hear it. How much slower the satellite clock is compared to the Earth's clock. I think I get what you're getting at. I feel like maybe the first one is flipped though. It feels like, or wait, no, this is less than one. Never mind. Maybe no, maybe you're right. Yeah, the clock in the inertial frame. That's what I figured. How much slower the satellite clock is than the Earth's clock. Okay, yes, and this number is less than 1. So that makes sense to me now. The denominator tells you how much slower the surface clock is than the Earth's clock. The same reason. Okay, and so it's almost like if you thought about it as like satellite divided by Earth divided by surface divided by Earth. It's almost like a cancellation, I guess. Okay. Thank you for that, BJFR. And welcome in, by the way. Subtraction of velocities was illegal. I think it was, yeah. So I wonder if we did use the if the velocity addition formula would have taken care of that for us. And we could have thought about the same way. Now that I understand, the book solution is a lot more direct than trying to do the addition of velocities thing. But I don't feel like going back through and doing it a third time. I think maybe this just needs to be automatic. When we see a problem, like identify what the inertial frame is. So I just kind of assumed that we were pretending we're in inertial frames. We definitely weren't. Yeah, I'm straying in it. There's like 34 lectures in the MIT Open Courseware series. And I think I just watched like 28. So I'm nearly done with this. Yeah, I learned about positive definite matrices and similar matrices in Jordan form. Let's just look at one. Why not? Yeah, that's what I was always intending when I started this linear algebra stuff. This is beyond where my linear algebra class already went. We never talked about positive definite stuff. I think it focused on linear transformations. I don't think we ever even talked about eigenvalues, or if we did, it was really brief. So yeah, the plan was to get through all the MIT stuff and then do a harder linear algebra, but now we're switching gears to the complex variables after this. So this is talking about a symmetric matrix and checking if it's positive definite by looking at subdeterminants. So just A, we're taking that as a positive, and we're taking that 2 by 2 determinant as positive. So the first sentence is saying. And then by manipulating this equation, we can say that, apparently. Okay, yeah. Lambda 1 and lambda 2 are the same signs. The product equals the determinant, right? And that's positive. The sign is positive because lambda 1 plus lambda 2 equals the trace. He actually said this in the lecture, now that I see it. Yeah, the product of the eigenvalues equaling the determinant and the sum equaling the trace is, you kind of use that to his advantage a lot to have a hacky, quick way of getting eigenvalues. It's kind of cool. Like when he's doing lectures, his intuition for like setting up the right matrix and stuff, it's kind of crazy what he can do on the spot. Just go through them one by one. I'm gonna bring in 2. Let's start with the first part of the question. So S1, that passes the test. Everything is well, wait. Determinant 35. Oh, no. S1 is not good. I was wondering about that because I thought S1 was good, and then that flies in the face of S1 being good, though. So S1 is not good. S2, 5 minus 4. Positive, trace is negative. So S2 isn't good either. S3 has at least one 0 eigenvalue. Well, are they both 0? Determinant 0, trace 101. Wait, how's that possible? Hey, Sage. It's going good. Donnie does DoorDash math. Hope you're doing well. S3 is confusing. Lambda 1, lambda 2 equals the determinant, which is 0, is it not? Yeah. Lambda 1 plus lambda 2 should equal the trace, though. This has no solutions. Yeah, I guess it definitely doesn't have positive eigenvalues. I'm gonna actually. I want to actually compute the eigenvalues of that because I'm confused by trying to use the tricks there. Hey, Anders. What is that? Oh, Frograve, nice. This one, positive determinant, positive trace. So only S4 checks out. None of the other ones do. S3, I need to see its eigenvalues. Oh, I'm stupid. I see it now. The other one's 101. I don't know why that wasn't clicking in my head. Okay, never mind. Carl? I have no clue what you're talking about. Sylvester criteria? I haven't heard it by that name. I'm using the product of the eigenvalues equals the determinant in the sum equals the trace. Oh yeah, I learned about that. Oh yeah, I guess we could have done it that way too. Fair, yeah. I was using these, but yeah, you're right. We could have done the subdeterminants. Okay, so I think we answered part 1. Part 2 is to do that. I want it to be negative. I'm just gonna try that. Why not? Noticing this column is slightly more than that column, so I'll put the -1 on the bottom. Any topic question? Any topic I can answer. So like a first year undergrad and below, I'd say. Oh, I got 0 here, didn't I? I did. Maybe I just make that a 2 though. -7. -8. I'm even more off now. Damn it. Do I want -1 too? Should I flip the signs? What is the test for positive test eigenvalues? Well, you can have positive pivots, you can have positive subdeterminants, you can look at the determinant and trace, or you can do the thing that I'm doing here with guessing and checking. This is an X transpose. -5 plus 12 is 7. -6 plus 14. Dude, this is so annoying. How do I do this? You have matrix and you want to apply a function f of x all its elements. Ooh. Yeah, f of a I think would mean, well, let me copy this onto the screen. So I think someone else might be able to answer this better. I need to think about that. Let's say define f of a. No, so if we said f of a is equal to like a squared, and a is a square matrix, that would give you matrix multiplication rather than squaring individual terms. You'd have to define what sign of a matrix means. You could probably do that with power series. Oh wait, but yeah, if you want to do the signs of the elements individually, I don't know how you would know that. Could we? Okay, if we pretend. Oh no. I don't know the notation for that if there is one. Typically, the only element-wise operations we do, I think, are just scalar multiplication. I feel like we don't usually do other operations to matrices element-wise. That, as far as I'm aware. For your machine learning program, cosine similarity between vector spaces. Hmm. Yeah, Jesu, what Papadori is saying is Papadori has a matrix and wants to take cosine of all of the elements and wants to know how to know that. Oh, okay. So I think this is the same question that Papadori has. Hey, actually, it's for a neural network. Um, and so you can just do that, I guess, for all ij. Hey, Alvito. Apparently, function composition, but W is a matrix, isn't it? But yeah, but I think this idea still works. Take f of each of the elements. This one is a little bit weird to me. What the hell? I'll link if you want to see that more, but that one's getting a little crazy. So yeah, I think it's best I got for you, Papadoria. I don't know how to say your name. I don't know that I can do your problem either. You'll give it a shot? Okay. Joy Boy, I guess? Okay. Brooke? Okay. Oh, really, $10? I was just realizing I could have kept x and y generic and gotten the polynomial. I think it would be better than guessing and checking. So you worked out too? Okay. I guess I'm going to think about this one first before I go back to that, though. We have multiple calls for induction here. Okay. Well, no. No, no, no. X can't equal 1. I guess we're already... I think we need to exclude x equals 1 from the problem statement, too, I think. But other than that, I think we're okay. I'm going to write that little note in there. I was addicted to induction. Induction with inequalities is always kind of scary because inequalities usually involve some crazy steps of adding things completely out of the blue that are pretty hard to spot. You're right. K over 2. Thank you, Papadoria. Oh, you're doing that division? Hey, finished. Um, Pretty good. How about you? Is this x to the k minus 1? Shouldn't it be x to the k? Or maybe you mean that left-hand side. You must mean that left-hand side. Because I'm pretty sure this left-hand side is already x. That's already what we want. Or that's just like x to the k. Okay, okay. You're working from the assumption? I guess we could do that too. That's possible for induction. Okay. So you're saying the left-hand side is 1 plus x squared plus x to the k minus 1. And you want to add x to the k to each side, which I guess we could only do from the assumption. We can't add things to both sides in the proof statement. So the left side, we could collapse back into the proof, right? That's your idea with doing this? So I assume. What do we do here? Oh, AMGM stuff? I'm really bad with it. I don't really know AMGM. Maybe it's helpful there in some way. Think you got it? I didn't see that you put that before. I don't know how to do that, Mate. I'm sorry. I know AMGM is a really useful thing for proofs like this, but I'm bad at proofs like this. Saying x to the k plus 1. No, it's just posted in the YouTube chat. I feel like I can show the problem statement again here. You're trying to mess with that numerator there? Oh, I think I see where you're going with this. This seems clean. Let me leave this out a bit better. Because we can get x to the k plus x to the k minus 1 over x minus 1. And we can apply the assumption. We want that. Um, Oh, with brackets? Okay, I could see that. You need to do something else here, though, right? We need to do some inequality trickery. We want k minus 2. Check out math discussion. Why isn't the bot working? It should be fine. Why isn't it working for you? Something, do you have like a line break in your LaTeX or something? That's so weird. There must be something wrong with that. Is it? It's the dollar sign on the very end. There's an extra space. I guess that's what. Um, it was that dollar sign on the end there. I deleted the space, and that made it work apparently. Uh, this is ninth grade math in Romania. Still hard though. Wow, that's crazy. Yeah, and so this looks like a really helpful thing. I don't know how to progress with it though, to be honest. Let me see what Anders put though. The line break is weird. This right here should be over there, just to... Maybe I can just write it. It might be, hopefully that's readable on stream. Maybe I should make it bigger. I think... No, this is slightly different from Femox's idea. You factor the x out from those. Then those become 1. And now on that bit, you apply the induction hypothesis. Oh, you're using that x is greater than root x in this step. I think we need to hold x greater than 1, to be honest. For x greater than 0, that step wouldn't... I'm not sure that it's true for x greater than 0. I think it needs to be x greater than 1. Because I feel like we were going to get a similar step somewhere in here too. And that's running about that in my head. Maybe it's true for x greater than 0, but I don't see. I feel like it shouldn't be necessarily. And that gives you the exact thing that you want. Right? Oh wait, well the k+1 is factored. Wait, we're expecting k+1 in parentheses. Hey Triambek. That's nearly it though. Is there a small modification we can do? I'm not sure. Hey Desson. Anders, Don, Penzenter, and Zach want to understand categories. Are you able to collab? I do not want to understand categories. But hey, I saw you writing that. I'm just... I get lost in that stuff. I saw you wrote that. I don't know what we're thinking the AM and GM of. Like, it's like set theory with fancy language. You're not selling it for me. No, I think I'm going to be full up on stuff between general relativity and setting up the complex analysis. But it seems like Zach and Penn are pretty... They'd be legitimately interested. If it is the only way, then I just can't do the problem. Which is not a first for me. What do you... God. Please speak English. I feel like you're insulting me. Oh, maybe you're not insulting me. Okay. But like, like what Fenless idea is nearly there. I seem to be able to sell, like, I can definitely sell that x to the k is greater than or equal to x to the k over 2 if x is greater than 1. What I can't sell is x to the k minus 1 over 2 greater than or equal to x to the k over 2. Is it? Wait, maybe, is that true? No, this is a smaller exponent. It can't be true. So that's why I'm getting stuck with Fembox. Fembox's thing. This is the thing we want to prove. Malay fan, you're in sixth form UK and everything's gone straight over your head. Are you Mate? No, wait, no, you can't be. No, never mind. This is going over my head too. There's a person in the YouTube chat who says we can do this with arithmetic mean, geometric mean stuff, and I just had never learned that, and I get very confused every time someone brings it up. So we could go back to the poster's original idea of starting from the assumption, realizing the left-hand side is that, and then adding x to the k to each side. That gives us the left-hand side that we desire. We need to figure out the right-hand side. We can do anything smaller than this, which I had the same exact issue here as I ran into with femboxes. That I can make this smaller, but I can't make that smaller. Like, I don't want to make that smaller and that bigger. Oh, it just kind of feels like a dead end. I think I'm just gonna say that I'm stuck on this problem. It's only people are working on it still, so we can come back to it. But with the things that I know, I don't know how to progress with this one, I don't think. And I still want to figure out this linear algebra question. So yeah, Brooke, I think people are still working on it. So if you hang out for a bit, someone might come up with a solution, or you can even check the recording later, because the recordings do go up on YouTube. But I think I need to throw in the towel on that one. I'm not sure. Okay. You're dealing with LaTeX? Okay. So before I was working on that linear algebra. And rather than guessing and checking completely blindly, let's make it a quadratic. I know how it should look, but I just want to do out each step of the matrix multiplication here because I just kind of need to see it. Oops. There we go. That's how that works. And I knew it should result in this, but I needed to see it for myself. So this might be easier to guess and check with. So 1 and -1 nearly work. They give you 0 though. So it should be something around 1 and -1. Do we need to go to fractions? Maybe that's how we get this done. If I take 5 times 1 squared plus 12 times 1 times -1/2. The point being, if I tried to increase y, then this 7 was kind of outcompeting the 12xy. And I just kind of always letting y be my -1. -6. 7/4. That's not quite it though, right? Wait, maybe this is it. No, it's not. This is more than 1. It's nearly it. Should we go to 1/4? That's going to make the problem... No, that's not it either. Should x be negative? One has to be negative, one has to be positive. This is annoying. It's just like guessing and checking. I don't think there's an actual good way of doing this. Okay, 1 minus 1 is bad. What if I did 2 minus 1? Did I already try the one? I probably did. Just try it again, though. No, this is good, right? Yeah, that's negative. Okay. Now's the key. I thought I tried 2 minus 1, to be honest. Did I do it wrong? I must have. Okay. Or the 20... Oh my god, I don't know. Optimism. Oh my god. Okay, you know... I just repeated the 20 from the 5 times 4. If the answer involves fractions, I'm gonna be a little mad. Okay, I'm just guessing. What about 3 minus 2? Oh, that's positive 1. Bruh. Four minus 2? Nope, that's positive 2. Going the wrong direction. Okay, fuck this. This is how we're solving that. I thought it'd be easier to guess, but it's really not that easy, to me at least. You have nearly 250,000 coffee beans. Oh my god. No, that's the name of my Oh, factoring. It's the name of my channel points. Does it? Oh my god. Is it this? No, wait, that's not it. Ben, hey. Nothing much. How about you? I put too many 5s as well. You're saying 5x plus 7y times x plus y. Yeah, okay, fair enough. Geometry 1 report? Ooh. That's cool. Or is it possible it's like topology? Or maybe you're doing like non-Euclidean geometry and stuff. Oh no, I think you mentioned that you're doing like non-Euclidean geometry. Yeah. Implicit demonstration? Yeah. That's like a first Mr. Calc thing. I mean, you might be doing it in a different way. Or if it's like a geometry class. Oh, it's possibly you're doing differential geometry, actually. Which I barely know. So I guess implicit differentiation, as I know it, is if you have you use it when you can't isolate y, at least not easily. It's like if you have the equation of a circle, you can do implicit differentiation on this like I mean, I guess, okay, you could isolate y here and take the derivative with respect to x, or you can just take the derivative with respect to x of this thing right off the bat. So if I take d by dx of each side, that would be 2x, and then we take the derivative of y squared with respect to x, you get 2y dy dx, and then derivative of 1 is 0. And now you could isolate dy by dx to find out the derivative. Shit. That's not it. Minus x over y. Doesn't actually name it for some reason. Oh, okay. No worries, dude. So should I be trying like 7 over 5 or something? 490 more sheets. You sure could. Second order non-homogeneous differentials, dash and dots are kind of satisfying. Oh man, I'm the dots for derivatives make me kind of uncomfortable. I'm trying to find any negative number. And x and y that gives me anything that's negative. Rounds are doing first and second order non. Oh yeah, I read that. Calculate number of infinite decimals you can have within a number times the infinite amount of whole numbers. I have no clue what you're talking about, Urbus. I'm sorry. All right, see you, Ben. Thanks for saying hi. Good luck with your geometry stuff. I assume that's primes, Jasu. Okay. I think these points might do it. -5 plus 6. -1 plus 6 over 7. Fuck. Go back to 4. -1 plus 4. -1. Wait, what am I doing? That's -5. Wait, so I was right with the 6. Oh my god. -5 plus 6. Positive number. -1 plus 6 over 7. Negative number. That's a negative. Oh my god, finally. Now those estimation problems, 7 switch estimate number of piano tuners. Oh, I haven't heard of those, I don't think. You're saying 4 minus 3 works? 5 times 16 is 80. 12 times 4 is 48 times -3. (48 times 3). 144? Oh, because it's 12 times 12. Yeah, it's 12 times 12. Okay. 7 times 9. Oh, nice, Brooke. You just barely made the cut there with -1. I got -7, 6. Yeah, that should be equivalent. 6 minus 5. Okay. In the factored form? Oh, yeah, true. I like doing a lot of mental math, apparently. So we could have just read them off this 2x2 matrix instantly somehow. So Strang during the lecture did make a point that if you complete the square on this thing, it does line up with. Actually, we should try to complete the square on this, right? That's maybe what we were supposed to do. Completing the square with something with x and y, it kind of hurts my mind though. Especially because we have a 5 and a 7. Oh, that's terrible. Can Wolfram complete the square for us? Maybe completing the square isn't that good there. Oh, wait, no. I don't know. I'm just going to put it into Wolfram and see what it spits out. It might not be possible to complete the square if it's not a positive number. Maybe that's it. What does the solution say? I wonder if there is a trick like that. 6.5. Number 2. No, they just gets unchecked. I've heard dash as well. It's not as common, but I think I've heard it. There is a cool relationship, though, if it is positive definite. With the completed square. Let me see if you guys have an example in here. I don't know. Hey, Teller Marketing. Just lots of practice. Oh, dots for multiplication. I do that too. That's how I was taught. Okay, he only did it in the lecture. He didn't seem to do it in the book. Energy, I was curious about that too. Applications X transpose SX is the energy in the system. Requirement of positive energy gives another definition. Huh. Can I think of an example of that? I don't know. I don't think I can. No, it doesn't really say. It doesn't really say an example. Okay. I think we want to wrap things up. But is anyone still working on the induction problem? So I would hate to cut someone off, but I kind of want to wrap up the stream. It's a tricky one. Yeah, same. I was wondering if Anders might be able to come up with someone else, but I haven't seen anything, so. Feel like he almost got it. And it worked by induction? Okay. How about this then? If you do come up with anything, post it in the Discord if you don't mind. And Brooke, if you're listening, I'll show it at the very beginning of my next stream. If there is, if anyone does find anything, I'll show it right at the beginning of my next stream in 2 days. Sorry, no. It'll be on Tuesday in my time zone. It might, depending on your time zone, it might be on Wednesday, but yeah, just like when you can just like check the recording, Brooke, and if there's anything I'll show it at the very beginning. If you happen to pop in, just like ask me and I'll like tell you too. But okay. Thanks for bringing out and thanks for trying the question with me. Sorry I wasn't able to do it, but oh yeah, that works too. I'll post the problem statement in the Discord. Someone in the YouTube chat was saying that. I just don't know AMGM. The exact thing, it was Mate earlier. Mate said that. I'm so terrible with AMGM though that I don't know how or what that even means. Yeah. Well, welcome in, Brooke. It's good to have you. But okay. On the YouTube stream, I'm gonna cut it off here. Twitch will look for a raid. So Brooke, tell her marketing. Anyone who's here on YouTube, thanks for being here. I'll be back. St. Joe's saying AMGM also. Okay. For instance, who's here on YouTube, will be back in 3 days on Tuesday for me. So see you later, YouTube.